Hello and welcome to Sleepy Science. What if reality does not become clearer the deeper you look, but less real? What if the solid world around you, your body, your memories, the stars, time, space, and even the feeling of being you, is only the first layer of a much stranger structure hiding underneath? In this journey, we'll descend from level 1 to level 100, through a universe where most of existence is invisible. Space can stretch faster than light can cross it. Black holes turn reality into an information problem. Particles stop acting like objects. Empty space refuses to be empty, and your brain quietly builds the world before you ever notice. These are not myths or fantasies. They are real ideas from cosmology, quantum physics, neuroscience, and modern science. Ideas that suggest reality may be less solid, less direct, and less certain at every level. So if you're ready to watch the ordinary world fall apart layer by layer, tap like, hit subscribe, and step into the mystery with me. Because by level 100, the question may no longer be, what is reality made of? But, was reality ever what it seemed? Most of the universe is missing, and we only see the small part that glows. Before the universe ever feels mysterious, it first fools you by glowing just enough to seem understood. You look up at the night sky, and your mind naturally follows the lights. The stars, the pale river of the Milky Way, the distant galaxies captured by telescopes, the shining clouds where new suns are born. It feels as if light is showing you reality itself, as if the bright parts are the universe and the darkness is only empty space between them. But that is the first illusion. The glowing universe is only the small visible layer of something much larger. Nearly everything we can directly see belongs to ordinary matter, the kind that forms stars, planets, dust, gas, oceans, rocks, bodies, and eyes capable of looking back. Yet when scientists studied how galaxies move, how clusters hold together, and how light bends as it travels through deep space, they found that the visible matter was not enough to explain what was happening. Galaxies were spinning as if they were embedded inside invisible halos. Giant cosmic structures were forming as if unseen gravity had helped guide them into place. Light from faraway objects curved around regions that seemed to contain more mass than the glowing matter could account for. So the universe began to reveal itself not by what it showed, but by what it forced us to infer. This hidden substance is called dark matter, not because it is evil or magical, but because it does not shine, reflect, or absorb light in the normal way. We do not see it directly. We notice its gravity, the way you might notice an invisible hand by watching a curtain move. And beyond that lies an even stranger clue. The expansion of the universe is not simply continuing, but appears to be speeding up, as if space itself is being pushed outward by something we call dark energy. Scientists do not fully know what dark energy is, and that honesty matters. These names are not final answers. They are careful labels for real effects that our best observations keep pointing toward. This means the universe you see is not the whole universe. It is the illuminated edge of a deeper structure, a small bright vocabulary written on a page mostly made of silence. And there is something humbling in that. You are made from the rare part that can form atoms, stars, chemistry, warmth, memory, and thought. Yet your existence is surrounded and shaped by things you cannot touch or see. The lesson is not that science has failed. The lesson is that reality is bigger than visibility. The cosmos does not owe your senses a complete picture. It gives you clues, motions, shadows, bending light, drifting galaxies, and asks you to become patient enough to read what is not shining. So the next time you look at the stars, remember that you are not seeing the universe fully revealed. You are seeing the part of it that glows, while most of existence remains quiet, hidden, and powerful enough to shape everything you call real. Space can expand faster than light, without anything breaking the speed limit. Imagine two distant galaxies so far apart that the space between them is growing faster than any beam of light could ever cross. and yet nothing is actually racing through space faster than light. That sounds like a contradiction at first, almost like the universe has found a loophole in its own rules. But the key is hidden in one simple difference. Moving through space is not the same as space itself expanding. In everyday life, speed means an object traveling from one place to another, like a car on a road or a spacecraft crossing the dark. Einstein's speed limit applies to that kind of motion. No object, signal, or message can locally move through space faster than light. But the universe is stranger than a road. Space is not a fixed stage where galaxies simply fly around. Space can stretch, and when it stretches, it carries distant galaxies farther apart, without those galaxies needing to travel through space like rockets. You can picture it gently, not as an explosion, but as marks on a soft fabric that is being pulled wider. The marks are not sprinting across the fabric, yet the distance between them grows. If the fabric is large enough and the stretching happens across enough distance, two faraway marks can separate faster than light would be able to close the gap. Nothing nearby breaks the speed limit. No galaxy feels a cosmic wind pushing it beyond physics. The rule remains intact because each galaxy is still almost at rest relative to its local region of space, while the vast distance between regions keeps increasing. This is why some galaxies are already slipping beyond our future reach. Their light may still be arriving now, carrying ancient images from a time when they were closer, but the space between us and them has expanded so much that a signal sent today might never catch up. This does not mean light has become weak or slow. It means the path itself is growing while the light tries to travel it. The idea is quiet but deeply unsettling. The universe is not only filled with distant places, it is actively changing the meaning of distance. What you call far away is not just a measurement, it is a moving boundary. And when you understand this, the night sky becomes less like a map and more like a farewell letter, still reaching you from regions that may one day become permanently unreachable. Space can expand faster than light without breaking the speed limit because nothing is outrunning light through space. Space is simply growing between things, patiently, silently, on scales too large for human instinct to grasp. And maybe that is the lesson hidden inside cosmic expansion. Reality does not always break its laws to become impossible. Sometimes it obeys them perfectly and still becomes stranger than anything your mind was prepared to imagine. Black holes may turn reality into an information problem. A black hole is terrifying, not only because nothing can escape it, but because it seems to ask whether the universe is allowed to forget. At first, you might imagine a black hole as a cosmic trap, a place where stars, gas, dust, and even light fall beyond a border called the event horizon and disappear from view forever. But the deeper problem is not simply that matter vanishes from sight. The deeper problem is what happens to the information carried by that matter. The details of what it was, how it was arranged, what particles made it, what state it had before it fell in. In ordinary physics, information is not supposed to be destroyed completely. It can be scrambled, burned, hidden, mixed into smoke and heat. But in principle, the universe should still preserve the deep record of what happened. A burned book no longer looks like a book, yet the atoms and energy have not been erased from reality. But black holes seem to push this idea to its breaking point. Stephen Hawking showed that black holes may slowly give off faint radiation and lose energy over enormous spans of time. If a black hole can eventually shrink away, then a haunting question appears. When it is gone, where did the information about everything it swallowed go? If it was destroyed, quantum physics is in trouble. If it was preserved, then it must have escaped or been stored in some strange way we do not yet fully understand. This is the black hole information paradox, and it turns the darkest object in the universe into something more like a locked archive than a simple grave. Some ideas suggest that information may be encoded on the surface of the black hole, as if the edge contains a record of what fell inside. Others suggest that Hawking radiation may carry subtle traces, not random noise after all, but an extremely scrambled message. Nothing about this is fully settled in a simple everyday sense. And that uncertainty is exactly what makes it powerful. A black hole forces physics to ask whether reality is made only of objects, or whether the true currency of the universe is information, patterns, relationships, states, and records that must somehow survive even when matter loses its familiar form. So when you picture a black hole, do not imagine only a mouth in space. Imagine a question so dense that modern science still bends around it. It asks whether the universe keeps its memories. It asks whether destruction is ever complete, and it quietly suggests that what is most real may not be the thing itself, but the information that says what the thing was. The future has a limit. Some galaxies are already becoming unreachable. There are places in the universe that still appear in our telescopes, yet may already be beyond the reach of anything we could ever send. This is one of the quietest and most unsettling truths in cosmology. The future does not open forever in every direction. It has a horizon, not a wall you could crash into, not an edge of space, but a limit created by the way the universe expands over time. When we look far into space, we are also looking far into the past, because light takes time to travel. A galaxy whose ancient light reaches us tonight may look present, but the image is old, sometimes billions of years old. During all that time, the distance between us and that galaxy has continued to grow. And because the expansion of the universe appears to be accelerating, some regions are being carried so far away that even a signal moving at light speed, sent now or in the future, may never arrive. This does not mean those galaxies stop existing. It means they are slipping out of causal contact with us, becoming parts of reality that can still be remembered by old light, but not reached, touched, visited, or updated by any future message. The universe, then, is not only vast, it is slowly closing certain doors. In the far future, if intelligent beings still exist in our cosmic neighborhood, the sky may look lonelier than it does today. Many distant galaxies will fade from view as their light is stretched and weakened, leaving future observers with a smaller visible cosmos and fewer clues about the grand expansion that shaped everything. Imagine being born so late that the evidence for most of the universe has already disappeared from the sky. You might think your local group of galaxies is nearly all there is, not because you are foolish, but because the universe has hidden its earlier openness from you. That is what makes this idea so powerful. Knowledge itself depends on when you exist. We are living in a rare age when the universe is old enough to contain galaxies, stars, planets, and observers, but still young enough for the distant cosmos to be visible. We can still see the large-scale story before too many pages fade beyond the horizon. And maybe that should change how you feel about the night sky. It is not just scenery, it is a temporary archive. It is a message arriving before the sender becomes unreachable. Every distant galaxy is not only a place, but a deadline written in light. The future has a limit, and the universe teaches this without drama, without warning, simply by stretching the distance between what can know each other and what must eventually become silent. Gravity can make two people age at different speeds. Place one person high on a mountain and another close to the sea, and the universe lets them move through time at slightly different rates. It sounds too strange to belong to ordinary life, but it is one of the real consequences of Einstein's view of gravity. Gravity is not just a pull that keeps your feet on the ground. It is linked to the shape of space and time themselves. The stronger the gravity around you, the slower time passes for you compared with someone in weaker gravity. On Earth, the effect is tiny, far too small for your body to feel in a normal day. But modern atomic clocks are sensitive enough to measure it. A clock placed at a higher altitude, a little farther from Earth's mass, ticks very slightly faster than a clock closer to the ground. This means time is not one universal river flowing at the same speed for everyone. It is more like a local rhythm, shaped by where you are and how gravity surrounds you. The idea becomes extreme near very massive objects. If someone could safely remain near a black hole, while another person stayed far away, their clocks would disagree dramatically. The person closer to the intense gravity would age more slowly from the viewpoint of the distant observer. This is not fantasy. It is the same principle that must be considered in real technologies such as GPS satellites, where precise timing matters so much that even small differences caused by gravity and motion have to be corrected. Without those corrections, location systems would drift and become inaccurate. So the lesson is not only cosmic, but practical. Your phone can find you because physics understands that time is flexible. And when you sit with that idea, something quiet shifts in the way you see your own life. Time feels personal already, stretching during fear, vanishing during joy, slowing in boredom, speeding through memory. But beneath those feelings, nature itself also refuses to make time absolute. Two people can meet, part ways, live under different gravitational conditions, and return having aged by slightly different amounts. Usually the difference is almost nothing, but the principle is enormous. It means your body is not simply living inside time like a fish inside water. Your body is moving along a path through a universe where time is shaped by mass, distance, motion, and gravity. Every second you experience is local, intimate, tied to where you are in the fabric of reality. And maybe that is the most humbling part. Time is not a single clock hanging over the cosmos. It is woven into the world, bending quietly around planets, stars, and you. The universe has no center, even though everything is expanding. If every distant galaxy seems to be moving away, it is tempting to imagine that we must be sitting near the center of everything. But the universe is stranger than that because every observer, in every faraway galaxy, would see the same general pattern from their own sky. This is the quiet trick hidden inside cosmic expansion. It does not need a central point. The universe is not expanding outward from one special location, like fragments flying away from a broken object. Instead, on the larger scales, the distances between galaxy groups are increasing everywhere at once. A useful way to picture this is to imagine tiny dots drawn on the surface of a balloon as the balloon inflates. Each dot sees the other dots moving away, yet no dot on the surface is the center of the expansion. The center of the balloon exists only in the higher dimensional space of the analogy, not on the surface where the dots live. Our universe is not literally a balloon, but the lesson helps. Expansion can happen without any place inside the universe being the middle. This matters because your instincts were built for small things. Rooms, roads, explosions, maps, places with edges and centers. Cosmology asks your mind to let go of that habit. Space itself may be arranged in a way where every location can look central from its own point of view, while none is truly privileged. Even the observable universe has a center only in a practical sense. You are at the center of the region whose light has had time to reach you, just as another observer elsewhere would be at the center of their own visible bubble. That does not make Earth important in a cosmic way. It simply means observation always begins from where the observer is. So when someone asks where the center of the universe is, the answer is not hidden in some distant constellation. The deeper answer is that the question may be shaped by an old human expectation that everything vast must have a middle. The universe teaches something softer and more unsettling. Reality can expand without choosing a throne, can be immense without pointing back to one sacred spot, and can make every place look central while belonging fully to none. The Big Bang was not an explosion into empty space. The Big Bang was not a bomb going off in the dark because there was no empty stage waiting for the universe to explode into. That is the mistake many people carry without realizing it. They picture all matter squeezed into one tiny point, floating somewhere in blackness, and then suddenly bursting outward like fire from a cosmic grenade. But modern cosmology tells a stranger and more careful story. The Big Bang is not best understood as an explosion inside space. It is the rapid expansion of space itself from an extremely hot, dense early state. There was no outside room around it, no surrounding emptiness, no distant wall that the newborn universe expanded toward. Everything we can observe today was once compressed into a much hotter, denser condition, and as the universe expanded, it cooled, allowing particles, atoms, light, stars, and galaxies to eventually form. This means the Big Bang happened everywhere, not at one location. Every region of space was once part of that early dense state, and every direction we look carries evidence of that ancient beginning. One of the strongest clues is the cosmic microwave background, a faint leftover glow from the young universe, released when the cosmos had cooled enough for light to travel more freely. It is not the flash of an explosion seen from the outside. It is more like a fossil light, arriving from every direction, showing that the early universe was once hot and nearly uniform. And this changes the feeling of the story completely. The universe did not begin like a firework in a void. It began more like the stretching of reality's own fabric, with space, matter, radiation, and time deeply tied together in a state where our everyday images break down. Scientists can describe the universe back to an incredibly early, hot stage, but they are careful about saying what happened at the absolute first moment, because our current physics becomes uncertain there. That honesty matters. The Big Bang is not a finished answer to why anything exists. It is the best supported description of how the observable universe evolved from its earliest known condition into the vast structure we see now. So when you imagine the beginning, do not imagine a center, an edge, or a blast wave crossing darkness. Imagine every part of space once being closer, hotter, brighter, and more compressed than your mind can easily hold. Imagine reality not thrown into a container, but the container itself growing. And perhaps the deepest lesson is this: even the word beginning may be too simple for what happened. The Big Bang does not just tell us that the universe was once smaller. It teaches us that our most familiar ideas, place, emptiness, distance, outside, before, may not be strong enough to hold the origin of everything. Reality did not arrive in the way human imagination expects. It unfolded from a condition where the map, the road, and the traveler were all part of the same emerging mystery. A star you see tonight may no longer exist. Some of the lights above you are not objects you are seeing now, but messages that left their stars before your life, before your parents, before entire human civilizations rose and vanished. When you look at the night sky, it feels immediate, as if the stars are hanging there in the present, quietly burning while you watch. But light is not instant. It travels at a finite speed, and even though that speed is incredibly fast, space is so vast that every star you see is also a look into the past. The moon appears as it was a little over a second ago. The sun appears as it was about 8 minutes ago. Some bright stars in the night sky are seen as they were decades, hundreds, or even thousands of years ago. That means the sky is not a live image. It is a layered archive of different times arriving together in your eyes. Now, for many stars visible to the naked eye, especially the closer ones, it is very likely they still exist because stars often live for millions or billions of years. So it would be misleading to say every star you see is probably dead. But the farther you look, especially through telescopes toward distant galaxies, the more the idea becomes real. Some of the stars whose light reaches us may have already changed, exploded, collapsed, or faded long before their final news could ever arrive here. A massive star can die in a supernova, leaving behind a neutron star, a black hole, or expanding clouds of heavy elements. Yet if that star was far enough away, its old light may continue traveling across space long after the event itself has happened. You are not seeing the star as it is. You are seeing the star as it was when the light began its journey. This makes the night sky feel less like a ceiling and more like a memory system, where distance becomes delay and beauty becomes evidence of time. Every point of light carries an age. Every sparkle is late. And there is something deeply humbling in realizing that your eyes are not only looking outward, but backward. You are standing in the present while receiving ancient signals from places that may have already become something else. The universe does not update all at once. It reaches you slowly, patiently, one beam of light at a time. So when you look up tonight, remember, the sky is not lying to you, but it is not showing you the present either. It is showing you history still bright enough to arrive, A quiet reminder that reality is always deeper than the moment you think you are seeing. The same laws that build order also push the universe toward disorder. A snowflake, a living cell, and a burning star all carry the same quiet contradiction. Nature can build beautiful order while still pushing the universe toward disorder. At first, this feels wrong, because we often hear that everything tends to fall apart, that entropy increases, that the universe is slowly moving toward a more spread out and less usable state. But entropy does not mean that order can never appear. It means that when the whole system is counted honestly, energy tends to become more dispersed, less concentrated, and less able to do focused work. This is why a hot cup of tea cools into the room instead of the room's warmth gathering back into the cup. This is why perfume spreads through air instead of remaining in one perfect corner. Yet inside that larger drift, pockets of order can still form. A star becomes stable because gravity pulls gas inward, but that same star shines by releasing energy outward into space. A plant builds leaves, roots, and delicate chemical structures, but it does so by taking in sunlight and releasing heat into its surroundings. Your own body keeps itself organized every second, repairing cells, moving blood, balancing chemistry, and preserving a sense of life. But it can only do this by constantly using energy and sending waste heat and disorder back into the world around it. Order is not a rebellion against entropy. Order is often the path entropy uses to grow. That is the part that makes the universe feel almost poetic without becoming magical. The same physical rules that let galaxies form. Crystals grow, storms swirl, forests breathe, and minds think also ensure that energy keeps spreading. Gradients keep fading, and the future becomes different from the past. Entropy gives time its direction. You remember yesterday, not tomorrow, because the world leaves traces as order becomes harder to perfectly restore. Broken glass does not leap back onto the table. Smoke does not return neatly into the flame. And a life once lived cannot be rewound into untouched possibility. But this is not only tragic. Without the flow from concentrated energy toward dispersed energy, nothing would happen at all. No weather, no metabolism, no fire, no thought, no story. The universe creates temporary islands of structure because energy is moving through them. And in that movement, patterns briefly rise like shapes in flowing water. You are one of those patterns. Not separate from disorder, but made possible by it. So the strange lesson is not that everything simply decays. The deeper lesson is that beauty, life, memory, and complexity can appear because the universe is always spending something. Every ordered thing is a candle, not because it is meaningless, but because it shines by transforming what it has been given. And perhaps that makes existence feel more precious, not less. Order is temporary, but while it lasts, it can wake up, look around, and understand the law that is slowly carrying it away. Reality may be made of information before it becomes matter. Before a thing can be heavy, bright, hot, or solid, it may first have to answer a quieter question. What state is it in? This is where reality begins to feel less like a collection of objects and more like a language of differences. In everyday life, information sounds like something human. Words on a page, numbers on a screen, a message sent from one mind to another. But in physics, information can mean something deeper and more basic. It can mean the pattern that tells one possible reality apart from another. A particle here instead of there, a spin pointing one way instead of another, an atom arranged in one structure instead of a different structure. The same ingredients can become wildly different things depending on how they are organized. Carbon atoms can help form soft graphite, hard diamond, or the complex chemistry of living cells, not because the atoms are made of different magic, but because arrangement matters. Pattern matters. Information matters. Matter is not only stuff, it is stuff with a state, a position, a relationship, a history, a set of possibilities narrowed into something definite. This is why some physicists have wondered whether information is not just something matter carries, but something matter may depend on. John Wheeler captured this idea with the phrase, "it from bit," suggesting that what we call physical reality may arise from answers to basic yes or no questions, from distinctions that become structure. This does not mean the universe is literally a computer in the simple human sense, or that rocks are secretly made of internet data. That would be too easy and probably misleading. It means that when we strip reality down, we do not only find tiny objects, we find states, rules, relations, and measurable differences. A thing becomes meaningful in physics when it can be distinguished from other possibilities. Without information, matter would be like a book with ink, but no letters, a melody with sound, but no order, a face with features, but no expression. The physical world depends on more than ingredients. It depends on how those ingredients are specified. Even temperature, pressure, and energy are not just raw substances. They describe how countless parts are arranged and how they can change. When a system evolves, it does not merely move. It transforms information about its previous condition into information about its next one. And this is why the idea is so powerful. Perhaps reality is not built first as solid things that later acquire meaning. Perhaps what comes first is the deep structure of possible states, and matter is one way that structure becomes visible. You do not experience this directly because your senses simplify the world into objects. A table, a hand, a star, a stone. But underneath those familiar names are patterns so precise that changing the arrangement changes the thing itself. The universe may be teaching us that existence is not only about what is present, but about what is distinguishable. Something is real not just because it occupies space, but because it carries a state the universe can preserve, transform, or reveal. And if that is true, then reality is far more subtle than the solid world suggests. The deepest layer may not be matter sitting silently in space, but information giving matter its identity, its memory, and its form. What you touch may be made of atoms, but what makes those atoms become anything at all is the hidden order they carry. A simple rule can create chaos too complex to predict. One tiny change at the beginning can grow until the future becomes impossible to see clearly. That is the quiet shock hidden inside chaos. Not randomness, not magic, not disorder without rules, but a world where simple rules can produce behavior so tangled that prediction breaks down. You might imagine that if a system follows clear laws, then its future should be easy to know. Push something gently, measure it carefully, follow the pattern, and the answer should unfold like a straight road. But nature often refuses to be that simple. A dripping faucet, a swinging pendulum, a rolling current of air, the motion of weather, the spread of smoke, the rise and fall of animal populations. Many of these can be shaped by rules that are not complicated on their own, yet the results can become wildly sensitive to tiny differences. Start with almost the same condition, almost the same temperature, almost the same pressure, almost the same position, and after enough time, the outcomes can separate completely. This is why weather can be predicted for a while, but not perfectly far into the future. The atmosphere is not lawless. It is too connected, too responsive, too sensitive. A small disturbance can grow, meet other disturbances, fold into larger patterns, and eventually change the whole scene. This is sometimes called the butterfly effect, but the real lesson is deeper than the image of a butterfly causing a storm. The lesson is that knowing the rules does not always mean controlling the outcome. A system can be deterministic and still feel unpredictable because every detail matters more than your measurements can capture. And this reaches beyond weather. Your heartbeat has patterns that are not perfectly mechanical. Rivers carve branching paths from small differences in flow and ground. Crowds, markets, ecosystems, and even thoughts can shift because small causes amplify through networks of feedback. Chaos teaches that reality is not only built from laws, but from relationships between moments, where each step becomes the starting point for the next. It also changes how you think about your own life. A sentence you almost did not say, a place you almost did not go, a decision that felt too small to matter can later become part of a much larger pattern. This does not mean everything is fate, and it does not mean every tiny act controls the universe. It means the world is alive with sensitivity. Simple beginnings can become complex endings. Order can turn into turbulence without ever abandoning law. So when you look at a cloud twisting in the sky, water curling around a stone, or your own life changing from one small moment, remember that chaos is not the absence of structure. It is structure becoming too rich for the mind to hold all at once. A reminder that reality can obey simple rules and still remain beautifully, humblingly unpredictable. The universe looks smooth only because you are seeing it from far away. From close up, the universe is a wilderness of clumps, gaps, knots, and emptiness. But from far enough away, it begins to look almost strangely even. This is one of the most important shifts in cosmology. The universe does not look smooth because it is simple. It looks smooth because your view has been pulled back until the roughness starts to average out. On smaller scales, space is wildly uneven. Matter gathers into planets, stars, galaxies, galaxy clusters, and long glowing chains that form a vast cosmic web. Between those structures are enormous voids, regions so large and sparse that they make the universe feel less like a crowded ocean and more like a foam of bright islands separated by quiet emptiness. If you could travel through one small region of the cosmos, you would not see balance everywhere. You would see crowded neighborhoods and lonely deserts, dense knots of galaxies and stretches where almost nothing shines. But when astronomers map the universe across truly immense distances, a different pattern appears. No direction seems to be the special direction. No vast region seems to contain all the matter, while another contains none. The details are uneven, but the large-scale average becomes surprisingly uniform. It is like looking at a beach. Bend down, and you see individual grains, broken shells, tiny shadows, rough textures, and irregular shapes. Rise high enough above it, and the same beach becomes a smooth band of color. The smoothness was not fake, but it was not the whole truth either. It depended on scale. This teaches a quiet but powerful lesson. Reality changes character depending on how closely you look. What seems chaotic nearby can become orderly from a distance, and what seems smooth from far away can break into hidden structure when you zoom in. Cosmologists rely on this idea because it lets them describe the universe as a whole without tracking every galaxy one by one. They assume that, at the largest scales, the cosmos is broadly similar everywhere and in every direction, not perfectly, but well enough for the grand story to be studied. And this should make you question your own sense of certainty. How many things in life look simple only because you are too far away to see their inner structure? How many things look chaotic only because you are too close to see the larger pattern? The universe reminds you that smoothness is not always emptiness, and complexity is not always confusion. Sometimes the truth depends on the distance from which you are able to see it. Dark matter holds galaxies, together without ever showing its face. A galaxy should fly apart if you judge it only by the matter you can see, and that is where the invisible begins to feel stronger than the visible. Picture a spiral galaxy turning slowly in the dark, its arms filled with stars, gas, dust, and glowing regions where new suns are being born. If most of its mass were concentrated in the bright central region, then the stars near the outer edges should move more slowly, the way distant planets in a solar system orbit more gently than inner ones. That was the expectation. But when astronomers measured the motion of stars and gas in many galaxies, they found something strange. The outer regions were moving too fast, not just a little strangely, but in a way that suggested the galaxy contained far more mass than the glowing parts revealed. This became one of the strongest clues for dark matter. It is not seen as a shining object, not photographed like a star, not caught as a cloud-blocking light. It is inferred from gravity, from motion, from the way galaxies behave as if they are sitting inside large invisible halos. Vera Rubin's work on galaxy rotation helped make this problem impossible to ignore, because the pattern appeared again and again. Galaxies were not rotating the way visible matter alone predicted. Dark matter, if it exists as most cosmologists think, does not hold galaxies together like glue in a sticky, ordinary sense. It surrounds and permeates them gravitationally, adding mass to the system, deepening the invisible world that stars and gas move within. Without that extra gravitational influence, many galaxies would not have the same shapes, speeds, or long-term stability we observe. And yet dark matter remains deeply frustrating because it does not reveal itself through light. It does not seem to shine, burn, reflect, or absorb in the familiar ways. It leaves no face, only fingerprints. The stars become the witnesses. Their motions testify that something unseen is there. This teaches a different kind of seeing. Science is not only about what appears in front of the eye, but about what must be present for the visible world to behave as it does. A galaxy, then, is not just a bright spiral floating in space. It is a luminous pattern moving inside an unseen gravitational body, like dancers whose steps reveal the shape of a floor hidden beneath fog. And perhaps that is the quiet lesson dark matter gives us. The universe is not required to show its foundations. Sometimes, the deepest structure of reality is known only because everything visible is moving around it. The shape of space may decide how reality can exist. Reality may not only depend on what exists inside space, but on what kind of space is allowed to exist around it. This sounds abstract at first, because space feels like nothing more than emptiness, the invisible room where planets drift, light travels, and your body occupies a place. But in modern physics, space is not just a blank container. It can have shape, curvature, and global structure, and those features may decide what kinds of paths, patterns, and possibilities the universe can hold. On Earth, you are used to flat geometry in daily life. Two straight lines can stay the same distance apart. A triangle has familiar angles, and distance feels simple. But on a curved surface, those rules change. On a sphere, two paths that begin straight and parallel can eventually meet. A triangle drawn across a curved surface can behave differently from one drawn on a flat sheet. Now stretch that idea beyond surfaces and into the universe itself. Space may be flat on the larger scales, or it may curve in ways so subtle that we can barely detect them. It may extend forever, or it may be finite without having an edge, like a shape where traveling far enough in one direction could, in principle, bring you back without ever reaching a wall. Scientists test these possibilities by studying ancient light, galaxy patterns, and whether the universe's geometry leaves fingerprints in what we observe. So far, measurements suggest that the observable universe is very close to flat, but close to flat does not automatically answer everything about its full shape, because we may only see a limited region of something much larger. This matters because geometry is not decoration. The shape of space can influence how light travels, how distances behave, how structures appear, and what kinds of cosmic histories are possible. Even the question, how big is the universe, depends on geometry. A universe can be vast and finite or vast and endless, and your intuition may not be able to picture either one clearly. That is the strange beauty of this idea. Reality may be partly written not in objects, but in the rules of the stage itself. You can remove every star from your imagination, every planet, every galaxy, and still space would not become meaningless if its shape remains. It would still carry instructions about direction, distance, return, separation, and connection. And perhaps that is why this topic feels quietly unsettling. You live as if space is obvious because you move through it every day. But the deeper question is not only where things are, it is what kind of where the universe gives them. The shape of space may be one of the silent reasons reality can exist in the form you know, not as a painted background, but as the hidden grammar that tells every path how it is allowed to unfold. The universe may be more like a calculation than a machine. A machine is something you imagine with gears, parts and pieces pushing against each other, but the universe may be stranger than that. It may behave more like a vast calculation unfolding from one state into the next. This does not mean the cosmos is literally a laptop, or that stars are made of code in the simple way a video game is. That would be too shallow, and science does not require that claim. The deeper idea is more careful. Many parts of reality can be described as information changing according to rules. A falling stone, a spreading wave, a cooling gas, a magnetic field, a living cell. Even the light moving through a telescope can all be understood as systems whose present condition helps determine what they can become next. In the old machine picture, nature feels like a clockwork device, solid pieces interacting in a fixed mechanical order. But modern physics often makes the world feel less like metal wheels turning and more like patterns being transformed. A particle is not just a tiny bead sitting in a place. It has a state. A field is not just an invisible substance. It can carry values, changes, and relationships. A physical law is not a command shouted from outside the universe. It is more like a rule that tells reality how to update itself from moment to moment. This is why some scientists and thinkers are drawn to computational language. They are not always saying the universe is artificial. They are saying that beneath the visible drama of matter, there may be something rule-like, relational, and process-based. The world may be less like a finished object and more like an ongoing operation. What you call a planet may be a stable pattern in motion. What you call heat may be countless hidden motions being summarized. What you call matter may be a way deeper fields and states show themselves at human scale. The machine metaphor made sense when people looked at pulleys, clocks, and engines and saw nature through the technology of their age. Today, surrounded by information systems, simulations, and algorithms, we are tempted to see calculation everywhere. But the honest view stays balanced. The universe may not be calculating in the human sense, yet calculation may be one of our best ways of understanding how simple rules generate rich behavior. And this changes the way reality feels. You are not living inside a dead mechanism that merely grinds forward. You are living inside a continuous unfolding, where each moment carries enough structure to give birth to the next. The cosmos may not be a machine with a maker's label hidden somewhere behind the stars. It may be something quieter and more profound. A lawful transformation, a pattern that keeps becoming, a calculation with no screen, no keyboard, and no outside observer required to make it real. Light behaves like a wave until it is detected like a particle. Light becomes truly unsettling when you realize it does not behave like one simple thing waiting to be named. In one experiment, it spreads like a wave, creating soft bands of brightness and darkness, as if it has traveled through more than one path at once and overlapped with itself. In another moment, when it is caught by a detector, it arrives in tiny individual hits, like separate packets of energy landing one by one. This is the strange lesson of wave-particle duality. Light is not merely a wave pretending to be a particle, and not merely a particle pretending to be a wave. It is something deeper that our ordinary words divide too sharply. The famous double-slit experiment shows this clearly. When light passes through two narrow openings without any device checking which path it takes, the pattern on the screen looks wave-like, with bright and dark stripes formed by interference. But when the setup is changed so the path of each photon can be known, that interference pattern disappears, and the light behaves more like separate particles taking definite routes. The important point is not that a human eye magically controls reality. Detection means physical interaction. To measure which path the light took, the system must disturb or mark it in some way, and that changes what can appear later. The wave-like pattern depends on possibilities remaining able to overlap. Once the path information becomes available, those possibilities no longer combine in the same way. This does not make light fake or undecided in a mystical sense. It reveals that nature at small scales does not fit the categories built from everyday life. A water wave spreads, a pebble lands in one place. Light can show traits of both depending on how it is tested. And that should make you pause, because the world you trust was built by a brain that expects clean identities, this or that, here or there, object or motion. But at the quantum level, reality often answers according to the question asked of it. The experiment teaches something precise and humbling. What you can know depends on how you try to know it. Light is not confused. We are the ones using old language for a deeper behavior, and perhaps that is why this truth stays so powerful. A beam of light crossing a room seems ordinary. Almost gentle, yet hidden inside it is a reminder that reality is not required to match human intuition before it becomes real. Your sense of touch is mostly electrical repulsion. The most familiar feeling in your life may be built on a distance too small for you to notice. When your hand rests on a table, it feels obvious that skin and wood are touching, that one solid thing has met another solid thing. But at the deepest level, matter is not made of tiny hard marbles pressing flat against each other. Atoms are mostly structured by electric forces, with negatively charged electrons around them and positively charged nuclei at their centers. When the atoms in your skin come close to the atoms in the table, their outer electron clouds resist being pushed into the same space. They repel, rearrange, and create forces that stop your hand from passing through. What you experience as contact is really your nervous system translating that resistance into pressure, texture, weight, smoothness, roughness, warmth, or pain. The table does not need to merge with you for you to feel it. It only needs to push back through the invisible rules of electromagnetism and quantum behavior. Inside your skin, tiny receptors respond to deformation, vibration, temperature, and stress. They send electrical signals through nerves, and your brain builds the feeling of touch from those signals. This means touch is not a simple meeting of surfaces. It is a conversation between fields, forces, tissues, and interpretation. Even the softness of cloth or the hardness of stone comes from how atoms and molecules resist, bend, slide, or hold their structure when pressed. A pillow feels soft because its material yields and spreads the force gently. Metal feels hard because its atoms are locked into a structure that resists deformation. Your body reads these differences and turns them into a world you can navigate. This does not make touch unreal. It makes it more remarkable. The comfort of holding someone's hand, the shock of cold glass, the grain of wood beneath your fingers, the ache of pressure on your skin, all of it is real experience, but it is not what it seems on the surface. You are not touching reality in the simple way your senses suggest. You are feeling the boundary where matter refuses to overlap. You are feeling forces become sensation. And perhaps that is the quiet wonder hidden in every ordinary contact. The world feels solid not because it is packed with tiny unbreakable blocks, but because invisible repulsions are strong enough to become the feeling of presence. Reality has a speed limit. Reality has a speed limit because without one, cause and effect would lose their order. You can imagine the universe as a place where anything could send a signal instantly, where one event could influence another with no delay, where distance would become almost meaningless. But that is not the universe we live in. In modern physics, light in empty space marks the fastest speed at which information, influence, and physical signals can travel locally. This does not mean light is merely fast in the ordinary sense, like the quickest runner in a race. It means light speed is woven into the structure of space and time. The closer an object with mass gets to that limit, the harder it becomes to push it faster, because more and more energy is required. No rocket, stone, person, or message made of ordinary matter can simply accelerate past it. This limit protects the order of events. If information could travel faster than light, then in some situations, different observers could disagree about which event caused which, and reality would become dangerously tangled. A signal might appear to arrive before it was sent. A warning could reach you before the danger that created it. The universe seems to prevent this by placing a boundary around how fast cause can spread. And yet this boundary is not a prison in the simple emotional sense. It is what makes a stable story possible. It lets stars shine across distance, lets events unfold in sequences, lets the past leave traces before the future responds. Even your vision depends on this delay. You never see anything at the exact instant it happens. You see light that has traveled from the object to your eyes, whether from across a room or across deep space. The world feels immediate because nearby delays are too tiny for your senses to notice, but physics knows the truth. Every perception arrives after a journey. The speed limit of reality means the universe is not one single now shared perfectly everywhere. It is a network of events connected by signals that take time to move. This should make the ordinary world feel stranger, not colder. Every lamp, every face, every star, every motion reaches you through a lawful delay, and that delay is part of what keeps reality coherent. The speed of light is not just about light. It is the universe's way of saying that influence must travel, that causes need pathways, and that even reality must wait for itself to arrive. Your blind spot is filled in without you knowing. There is a hole in your vision right now, and the most disturbing part is that you cannot see it. Not because it is hidden far away, not because it is too small to matter, but because your brain quietly repairs it before your awareness ever notices the damage. Inside each eye, there is a place where the optic nerve leaves the retina, carrying visual signals from the eye toward the brain. This spot has no light-sensitive cells, no rods, no cones, no ability to detect the image falling on it. In that tiny region, your eye is blind. Yet when you look around the room, you do not see a dark patch floating in space. You do not see a missing circle in the wall, a gap in someone's face, or a black dot cutting through the world. Instead, your brain fills the blind spot using the surrounding information, stretching nearby color, texture, lines, and patterns across the missing area so smoothly that the world feels complete. If the blind spot falls on a plain blue wall, your brain paints in blue. If it falls on a simple pattern, your brain often continues the pattern. It is not giving you the raw truth. It is giving you the most useful version of the scene. You can reveal this with simple blind spot tests, where one eye is closed and a small dot disappears at just the right distance. Not because the dot stopped existing, but because its image landed on the part of the retina that cannot see. For a moment, the curtain lifts, and you realize your normal vision is not a perfect window. It is an edited experience, repaired in real time. This does not mean your senses are useless. In fact, it shows how powerful they are. Your brain is not trying to deceive you for no reason. It is trying to keep reality stable enough for you to move, reach, read, walk, and survive without being distracted by every flaw in the visual system. But the lesson is quietly unsettling. You can be missing information and still feel certain you see everything. Your confidence is not proof of completeness. The world you experience may feel seamless, but part of that seamlessness is constructed from educated guesses. And if your brain can hide a literal hole in your vision, you have to wonder how many other gaps in perception, memory, and understanding are being softened, patched, and smoothed over before you ever get the chance to question them. Particles can act like events, not objects. A particle may not be a tiny thing quietly traveling through the world, but a moment when the world answers a question. In ordinary life, an object seems simple. A stone remains a stone while it moves. A grain of dust stays itself as it floats. A ball follows a path even when no one is watching. So it feels natural to imagine electrons, photons, and other particles as extremely small versions of the same idea. Little pieces of stuff flying through space with hidden roots and private identities. But modern physics makes that picture less secure. In many experiments, a particle is not known as a miniature object you continuously watch from beginning to end. It is known through events: a flash on a detector, a dot on a screen, a tiny mark in a sensor, a transfer of energy at a particular place and time. The particle is what shows up when something interacts. Before that interaction, the best description may not be a solid bead with a definite path, but a spread of possible outcomes, a quantum state that tells us where and how the next event might appear. This is why physicists often speak carefully. A photon may be emitted by an atom, later absorbed by a detector, and between those two events, it is not quite like a bullet crossing a room. An electron can leave a track in a cloud chamber, but that track is really a chain of separate interactions, each one revealing a piece of evidence. like footprints in snow that make you imagine a continuous traveler. The path feels obvious after the marks appear, but the underlying quantum description is stranger than the path your mind draws. In quantum field theory, the world is described less as empty space, filled with tiny pellets, and more as fields that can gain and lose excitations. What you call a particle can be a localized happening in a field, a measurable disturbance, a packet of energy and properties that becomes real to us through interaction. This does not mean particles are fake. It means the word object may be too heavy, too classical, too shaped by tables and stones. At small scales, reality may be built from happenings more than things, from interactions more than permanent little bodies. And once you understand that, the universe begins to feel less like a warehouse of objects and more like a living record of events. Matter is not merely sitting there. It is appearing, exchanging, responding, revealing itself through contacts. You too attempted to think of yourself as a fixed object moving through time, but your physical existence is also a storm of events. Signals firing, molecules binding, light scattering from your skin, atoms exchanging energy with the world around you. The deepest lesson is not that nothing exists, but that existence may be more active than it looks. A particle is not always best imagined as a tiny marble. Sometimes it is better understood as reality making a mark, a brief, precise answer in a universe that speaks through events. You do not hear pure sound. Your brain interprets vibrations. A sound does not enter your mind as sound. It enters as motion, pressure, and vibration, and only later becomes the world you think you hear. When someone speaks your name, when rain taps a window, when music fills a dark room, it feels as if sound itself is traveling into you fully formed, carrying meaning, emotion, distance, and texture. But the outside world does not contain sound in the way your experience suggests. Out there, before your brain touches it, sound is a pattern of vibrating air, tiny changes in pressure moving outward from a source. A guitar string shakes, a vocal cord pulses, a door closes, and the surrounding air is compressed and released in waves. Those waves reach your ear, but your ear does not simply receive a finished experience. It transforms motion into biology. The eardrum vibrates. Tiny bones in the middle ear amplify that motion, and deep inside the cochlea, fluid waves bend delicate hair cells that convert mechanical movement into electrical signals. Only then does the brain begin its quiet work of interpretation. It separates pitch from loudness, location from tone, speech from background noise. It decides whether a sound is near or far, friendly or threatening, familiar or strange. It can even fill in missing pieces, allowing you to understand a sentence in a noisy room when parts of the sound never reached you clearly. This means hearing is not passive. It is construction. Your brain does not record the world like a microphone. It organizes vibration into meaning. That is why the same sound can feel peaceful in one context and frightening in another. A soft creak in the afternoon may mean nothing, but the same creak at night can become a warning because your brain listens with memory, expectation, and emotion. Even silence is not simple. In a perfectly quiet room, many people begin to notice their own breathing, heartbeat, or a faint ringing produced by the nervous system itself. The brain is always searching for pattern, always trying to turn vibration or the absence of vibration into a usable story. And this should make ordinary hearing feel strangely intimate. The voice of someone you love is not just air moving. It is air reshaped by your ear, translated by nerves, and given emotional weight by memory. Music is not only waves in a room, it is the brain turning rhythm and frequency into feeling. So when you hear the world, you are not receiving pure sound. You are experiencing a collaboration between physics and consciousness, between moving air and a mind that knows how to turn motion into presence. The vacuum has fields even when particles are gone. An empty room is never as empty as it feels, because modern physics does not treat emptiness as a perfect nothing, but as the lowest possible state of something still present. When you remove the air, the dust, the light, the heat you can easily measure, and every ordinary particle you can imagine, you might picture a silent blankness left behind, a clean stage with no actors. But quantum field theory suggests a deeper picture. The fields of nature do not disappear when particles are gone. They remain spread through space, even in what we call a vacuum. A particle, in this view, is not always a tiny object placed into an empty container. It can be understood as an excitation of a field, a little localized disturbance, like a ripple on a surface that was already there. Remove the ripple, and the surface has not stopped existing. In a similar way, remove particles, and the underlying fields still remain in their quietest available condition. This does not mean the vacuum is packed with ordinary stuff, and it does not mean tiny particles are literally popping in and out like sparks in a magical fog. That image can be useful as a metaphor, but it can also mislead. The more careful truth is that the vacuum has structure. It has a ground state. It can influence real physical effects, such as tiny shifts in atomic energy levels and forces that appear between very close surfaces under special conditions. The vacuum is not a place where physics has ended. It is a place where physics is still quietly active beneath the threshold of ordinary perception. This changes the meaning of nothing. In daily life, nothing means absence. An empty cup, an empty road, an empty shelf. But in fundamental physics, empty may only mean that no detectable particles are present in the usual sense. The fields are still there, capable of being excited, capable of shaping what particles can exist and how they behave. You live inside this invisible field-filled reality every second, but your senses are built for tables, air, warmth, sound, and light, not for the silent background conditions that make those things possible. So the vacuum is not a dead void. It is more like the quiet floor of reality, not speaking loudly, not glowing, not offering itself to your eyes, yet still carrying the rules from which visible things can rise. And perhaps that is the strangest lesson. The universe does not need to be full of objects to be full of presence. Even when the particles are gone, the fields remain, waiting in stillness, proving that the deepest kind of emptiness may not be nothing at all. Your brain predicts the world before it receives the full signal. Your brain does not wait for the world to arrive. It guesses first, then corrects itself with whatever evidence comes in. This may be one of the most surprising truths about perception, because it means you are not simply receiving reality like a camera receives light. You are living inside a constant negotiation between what your senses report and what your brain expects to find. Every second, signals from your eyes, ears, skin, and body are incomplete, delayed, noisy, and limited. If your brain waited for perfect information before building experience, you would move too slowly to survive. So instead it uses memory, context, pattern, emotion, and past experience to prepare a version of the world before the full signal arrives. When you walk into your kitchen in the dark, you do not need to analyze every shadow from zero. Your brain already expects the table to be where it usually is, the doorway to be shaped a certain way, the floor to continue beneath your feet. When someone speaks in a crowded room, you can often understand words even when parts of the sound are covered by noise, because your brain is not only hearing, it is filling, comparing, and anticipating. This process is often called predictive processing, and it does not mean your brain is lying to you. It means your brain is trying to be fast enough to keep you alive. The world changes quickly, and the nervous system has to act before certainty is complete. A ball flying toward your face, a car braking ahead, a sudden movement in the corner of your eye. In these moments, prediction is not a luxury. It is survival. But the same power that helps you move through the world can also distort what you experience. If you expect danger, a harmless sound may feel threatening. If you expect rejection, a neutral expression may look cold. If you expect pain, the body can become more sensitive before anything truly harmful happens. Your brain does not build reality from raw data alone. It weighs incoming signals against expectation, and sometimes expectation becomes heavy enough to bend the final experience. This is why perception feels so immediate even though it is partly constructed. You are not seeing a finished world and then reacting to it. You are meeting the world halfway, bringing a silent forecast to every moment, and perhaps that should make you gentler with your own certainty. What feels obvious may be partly predicted. What feels present may be partly prepared. The brain is not a passive window. It is an active storyteller trying to stay one step ahead of reality. And your experience is what happens when the story it expects meets the evidence that finally arrives. The same object can feel different, depending on context. A single object can seem to change without changing at all, simply because the world around it changes the way your brain understands it. Hold a grey square against a dark background and it may look lighter. Place the same grey against a bright background and it may look darker. Put your hand in cold water, then move it into lukewarm water, and that same lukewarm water may feel warm. Place your other hand in hot water first, and the same lukewarm water may feel cool. The object did not transform. The temperature did not secretly become two different temperatures. The color did not rewrite itself. What changed was the context, and your brain is deeply sensitive to context because it is not built to measure the world like a laboratory instrument. It is built to compare, to judge relationships, to ask, compared to what? This is why perception is always partly relative. A room can feel quiet after a loud street, but noisy after deep silence. A small hill can feel steep after a long walk, but gentle when you are rested. A face can look kind or threatening depending on lighting, memory, mood, and expectation. Even weight can feel different depending on size. A small object that is heavier than expected may feel strangely dense, while a larger object with the same weight may feel lighter than your brain predicted. Scientists study effects like this because they reveal that perception is not a direct measurement of isolated things. It is an interpretation of things inside situations. Your brain constantly uses surrounding clues to stabilize experience. Shadows help it decide color. Nearby objects help it judge size. Prior sensations help it judge temperature. And emotional state helps it judge meaning. This is not a weakness. Without context, the world would be harder to navigate. You would not know whether a surface is bright because it emits light or because sunlight is falling on it. You would not judge whether a sound is close or distant, whether a smile is sincere or nervous, whether a step is safe or slippery. Context gives the brain a frame, and the frame changes the picture. But the unsettling part is that you rarely feel the frame. You feel the conclusion. You believe the object simply is the way it appears. And this is where reality becomes more fragile than it seems. What you call the thing itself is often the thing plus its surroundings. The thing plus your body state, the thing plus your memory, the thing plus the hidden comparisons your brain has already made before you notice anything. So the lesson is not that nothing is real. The lesson is that experience is relational. The same object can become heavier, brighter, colder, safer, stranger, or more beautiful depending on the invisible context around it. And perhaps that should make you more careful with certainty, because sometimes what changed was not the world in front of you, but the frame through which your mind learned to see it. Quantum physics breaks common sense at the smallest scales. Common sense begins to fail the moment reality becomes too small for your hands, your eyes, and your everyday instincts to follow. In the world you live in, objects seem to have clear locations, clear identities, and clear histories. A cup is on the table, or it is not. A stone follows one path when it falls. A door is open or closed. This way of thinking works so well at human scale that it feels like truth itself. But quantum physics reveals that it is only a local habit, a rule of thumb shaped by large objects, warm environments, and slow senses. At the smallest scales, nature does not behave like a collection of tiny familiar things. It behaves according to rules that are precise, tested, and deeply successful, yet almost impossible to picture with ordinary imagination. An electron is not simply a miniature planet orbiting a tiny sun. A quantum system does not always carry every property in a definite way before it is measured. Possibility is not merely ignorance, it becomes part of the physical description. In some experiments, What can happen must be treated as a spread of potential outcomes, and only interaction with the wider world produces the single result you finally observe. This is why quantum physics feels so strange. It does not break because it is vague. It breaks your intuition because it is accurate in a region your intuition was never built to handle. Your brain evolved to throw stones, avoid danger, recognize faces, and move through solid surroundings. It did not evolve to imagine probability waves, uncertainty, or systems whose measurable features depend on how they are tested. Yet without these strange rules, the ordinary world would not exist in the form you know. Atoms would not have stable structures. Chemistry would not work the way it does. Materials would not have their familiar properties. The light from screens, lasers, solar panels, semiconductors, and medical imaging would not make sense without quantum principles behind them. The weirdness is not locked away in distant laboratories. It quietly supports the technology around you and the matter inside you. The mistake is thinking that common sense is the deepest layer of reality. Common sense is more like a simplified map, useful for walking through the visible world, but not detailed enough for the foundations beneath it. Quantum physics asks you to accept something humbling. Reality is not obligated to be imaginable before it is real. The universe can be lawful without being intuitive. It can be understandable through experiment and mathematics, while still resisting the pictures your mind wants to draw. And maybe that is the real lesson at the smallest scales. Nature is not confused. We are simply meeting a level of the world where the language of everyday life becomes too blunt, and where truth survives even after common sense falls apart. You do not see the world directly, you see a reconstruction. You never meet the world in its raw form. You meet the version your brain has already translated for you. This is difficult to feel because vision seems immediate and honest, as if your eyes open and reality simply pours in. But your eyes are not windows in the simple sense. They are living sensors that catch light and convert it into electrical activity, and from there, the brain must build the experience you call seeing. The outside world does not arrive as trees, faces, depth, color, motion, and meaning. It arrives as scattered signals, different wavelengths of light, shifting contrasts, edges, shadows, and changes across the retina. Your brain then organizes those signals into a stable scene. It decides where one object ends and another begins. It estimates distance from tiny differences between the two eyes. It creates the feeling of depth from flat images. It separates movement from stillness, recognizes familiar shapes, and attaches names and meanings before you consciously think about them. You do not see a chair as a collection of light patterns. You see chair because your brain has already turned sensation into interpretation. This reconstruction happens so quickly that you mistake the final model for the world itself. And yet the model is not a perfect copy. It is selective. Your brain sharpens what matters, softens what does not, ignores some details, emphasizes others, and uses memory to guess what should be there. This is why a shadow can look like a person for 1/10 second. Why a familiar face can appear in a pattern. Why a moving object may seem continuous even though your eyes jump in rapid bursts from point to point. The world you experience is not fake, but it is processed. It is more like a live translation than a direct recording, and every translation makes choices. Your senses give the brain evidence, but the brain gives that evidence structure. It creates a usable reality, not an unlimited one, because unlimited detail would overwhelm you. You need a world you can act inside, not a perfect inventory of every photon and surface. That is why perception is useful before it is complete. It helps you reach for a cup, read emotion in a face, avoid danger, follow movement, and recognize home. But the price of that usefulness is humility. What feels obvious may be edited. What feels direct may be assembled. What feels like the world out there is actually the world after passing through the quiet architecture of your nervous system. So when you open your eyes, you are not simply seeing reality. You are seeing reality rebuilt into a form your mind can survive, understand, and call real. Gravity is not really a force in Einstein's picture. Gravity feels like a force because your body is always being stopped from taking the path it naturally wants to follow. Stand on the ground and you feel weight pressing through your feet, as if Earth is pulling you downward with an invisible hand. That picture works well enough for everyday life, and Newton's description of gravity as an attractive force remains incredibly useful for calculating many motions. But Einstein's deeper picture changes the meaning of the pull itself. In general relativity, gravity is not treated as an ordinary force reaching out through space like a rope. Instead, massive objects such as planets and stars change the geometry of space-time, and other objects move along the straightest possible paths within that curved geometry. The strange part is that those paths can look curved to us. The moon does not orbit Earth because it is being yanked sideways in the simple way a ball on a string is yanked. It is moving through curved space-time, following a natural path that keeps bending around Earth because Earth's mass has reshaped the stage around it. A falling object is not being forced downward in Einstein's view. In a sense, it is doing the most natural thing it can do. It is the ground that interrupts that fall. When you stand still, the surface of Earth pushes up on you, preventing you from following the free-fall path your body would otherwise take. And that upward push is what you feel as weight. This is why astronauts in orbit feel weightless, even though gravity has not disappeared. Earth's gravity is still strong where they are. They are weightless because their spacecraft, and everything inside are all falling together around Earth, constantly missing the ground. Nothing inside the spacecraft is being pressed against a floor in the ordinary way, so the familiar feeling of weight vanishes. This idea is not just poetic. It has been tested through the bending of starlight near the sun, the timing of signals near massive bodies, the behavior of planets, and the gravitational waves detected from distant cosmic collisions. Einstein's picture teaches that gravity is not merely something objects do to each other, but something matter and energy do to the shape of reality itself. And that should make even standing still feel strange. The floor beneath you is not simply supporting a body in a force field. It is stopping you from moving along the curved path space-time has quietly offered you. What you call gravity may be the feeling of being held away from your natural fall. A reminder that reality is not a flat stage with forces painted on top, but a flexible structure where motion, mass, space, and time are woven together so deeply that even down becomes a geometry you can feel in your bones. Your body is rebuilt, while you still feel like the same person. Your body keeps changing its material, while your mind keeps calling it me. This is one of the quietest mysteries of being alive, because you do not wake up each morning feeling like a different organism, even though inside you, countless parts are being repaired, replaced, broken down, rebuilt, and renewed. Your skin sheds cells and grows new layers. Your blood is constantly refreshed. The lining of your gut renews quickly because it faces food, acid, microbes, and chemical stress every day. Your bones may feel like fixed stone, but they are living tissue, slowly remodeled by cells that remove old material and lay down new structure. Even many of the molecules inside your cells are temporary workers, assembled, used, damaged, recycled, and replaced. But this does not mean the simple claim that every atom in your body is replaced is perfectly true in every case, because biology is more uneven and more interesting than that. Some cells last a very long time. Many neurons in your brain can remain with you for most of your life, and parts of the lens in your eye can preserve proteins from very early in your development. Your body is not rebuilt like a house demolished and constructed again from nothing. It is more like a city that stays recognizable while roads are repaired, walls are repainted, wires are replaced, water systems are renewed, and old buildings remain beside new ones. The pattern continues even as the material changes. That is the important part. You feel like the same person not because every piece of matter stays the same, but because the organization, memory, nervous system, habits, relationships, and body maps keep carrying continuity forward. Life is not a frozen object. It is a process maintaining itself across time. Food becomes you. Air becomes part of your chemistry. Water enters, moves through you, and leaves. Cells divide, proteins fold, tissues heal, and your body quietly negotiates with the world every second to keep your temperature, blood chemistry, immune defenses, and energy balanced. This makes identity feel stranger than a mirror suggests. The face you recognize is stable enough to belong to you, but not static enough to be a permanent thing. The body you protect is not a possession you hold unchanged. It is an ongoing event, a living pattern constantly borrowing matter from the planet and returning it again. And maybe that is why being alive feels both fragile and miraculous. You are not the exact same collection of particles you once were, yet something real continues through the change. The you that remains is not a single unchanging substance, but a continuity of form, memory, and motion. A flame that keeps its shape while the fuel is always passing through. A memory can feel real, even when it has been rewritten. A memory can feel like a perfect recording, even while your brain is quietly editing the tape. You may think remembering means opening a sealed file from the past, replaying it exactly as it happened, and trusting the emotional weight because the scene feels vivid. But memory is not a stored video waiting untouched in a dark room. It is a reconstruction, rebuilt each time you bring it back into awareness. When you remember a birthday, an argument, a childhood room, or the face of someone you miss, your brain pulls together fragments, images, emotions, sounds, meanings, body sensations, and later knowledge you may not have had at the time. Then it assembles them into something that feels whole. The strange part is that the act of remembering can make the memory change. Neuroscience calls this process reconsolidation. When a memory is reactivated, it can become temporarily flexible before being stored again. That flexibility is useful because it allows memory to update with new understanding. A frightening experience can become less powerful after therapy. A confusing moment can gain meaning years later. A painful memory can be softened when seen from a safer place. But the same flexibility also means memories can absorb mistakes. Details can shift. Confidence can grow even when accuracy weakens. A story told many times can become smoother, more dramatic, more certain, until the version you remember is partly shaped by the telling itself. This is why eyewitness memories can be unreliable, especially under stress, suggestion, or pressure. It is not because people are always lying. Often they are sincerely remembering something that their brain has rebuilt imperfectly. Emotion makes this even more powerful. A memory tied to fear, shame, love, or grief can feel intensely real because the body reacts as if the past has returned. Your heart tightens, your stomach shifts, your mood changes, and the vividness convinces you that the memory must be exact. But vividness is not the same as accuracy. Feeling real is not proof that every detail is true, and this should not make you distrust your entire life. It should make you more careful, more humble, and maybe more compassionate. Your past is not a museum of frozen scenes. It is a living archive, constantly touched by who you are now. You carry real experiences, real wounds, real joys, but the shape of those memories can move as you move. So perhaps memory is not only a record of what happened, it is also the mind's attempt to keep the past meaningful, enough for the present self to survive it. The universe has no absolute up or down. Up and down feels so obvious that you almost forget they are not written into the universe. From the first moments of life, your body learns direction through gravity. Down is where things fall, where your feet press, where your weight settles. Up is where smoke rises, where birds fly, where the sky opens. But this sense of direction is local, not cosmic. It belongs to your position near Earth, not to reality as a whole. On the other side of the planet, another person's down points in almost the opposite direction from yours, and neither of you is wrong. Both of you are simply being guided toward Earth's center by gravity. If you floated far from planets, stars, and moons, with no floor beneath you and no familiar horizon, the idea of up and down would begin to dissolve. You could rotate your body, turn a spacecraft, or drift in any orientation, and physics would not suddenly mark one direction as the true top. Space has directions, but it does not have a universal ceiling or floor. This is difficult for the human mind because our senses evolved on a surface, under gravity, with ground below and sky above. We built language, maps, buildings, and emotions around vertical experience. We say people rise in status, fall into sadness, look up to heroes, and sink into despair, because our bodies taught our minds that height carries meaning. But the cosmos does not share that metaphor. A galaxy is not really above another galaxy in any absolute sense. A nebula is not hanging over the universe. A photograph of space can be rotated upside down, and nothing physical has been violated. The orientation is chosen by the observer, the camera, or the convention of the image. Even Earth itself has no true top. North is not naturally higher than south. It is a direction on a rotating planet, useful for navigation, but not a sacred vertical truth. This does not make direction meaningless. It makes direction relational. Up and down appear when there is a body, a gravitational field, a surface, a frame of reference, a point of view. Without those, the universe does not need them. And perhaps that is the deeper lesson hidden inside a very simple feeling. Some of the truths that seem most certain are really agreements between your body and your environment. You feel grounded because Earth gives you a direction, but the larger universe is not built around that comfort. It stretches in all directions without placing a throne above or a pit below. So when you stand under the night sky, you are not looking up in any cosmic final sense. You are looking outward from the surface that taught you what up means, into a universe where direction depends on where you are, how you move, and what you are using as your ground. Observation can change what is being measured. The moment you try to know something perfectly, your act of knowing may become part of what happens next. This is one of the strangest lessons in science, because we like to imagine measurement as harmless, as if the universe is a sealed glass box and we are only looking through the window. But measurement is never pure distance. To measure anything, something must interact with it. A thermometer has to exchange heat with what it measures. A camera must receive light from a scene. A radar signal must bounce off an object. Even in ordinary life, watching can change behavior. A person may speak differently when they know they are being recorded. A child may act differently when a teacher is watching. A delicate system may shift when touched by the tool meant to study it. But at the quantum scale, this idea becomes far deeper and more precise. Tiny systems are so sensitive that the very interaction needed to gain information can change the state being measured. If you want to locate an electron, you cannot simply see it the way you see a chair. You must interact with it in some physical way, and that interaction can disturb its motion or alter what can be known afterward. This is not about human consciousness magically shaping reality with thoughts. It is about physical contact, exchange, and entanglement between the measuring device and the thing being measured. The observer in physics is not always a person. It can be an instrument, an environment, or any interaction that forces a system to leave behind a definite trace. Before measurement, a quantum system may be described by a range of possible outcomes. After measurement, one result appears, and the possibilities that once had to be considered together no longer remain available in the same form. This is why observation is not always passive. It can be a doorway that reality must pass through, and the doorway changes what comes out on the other side. The deeper lesson is not that truth is impossible, but that truth sometimes depends on the method used to reveal it. What you ask, how you ask, and what you use to ask can shape the answer you receive. Science becomes powerful not by pretending measurement is invisible, but by understanding exactly how measurement changes the situation. And perhaps this should make you more humble about everything you think you simply observe. The world is not always waiting untouched for your gaze. Sometimes, to learn something, you must enter the system, and the moment you enter, the system is no longer exactly what it was before. Your brain can hide something right in front of you. You can stare directly at something and still fail to see it, because vision alone is not the same as awareness. This is one of the most unsettling discoveries about the mind. The world can be physically present in front of your eyes. The light from it can enter your retina. The signal can reach your brain. And yet you may experience nothing at all if your attention is elsewhere. Attention is not just a spotlight that makes things clearer. It is more like a gatekeeper deciding which parts of the scene are important enough to become conscious. A famous example comes from studies of inattentional blindness, where people asked to focus on a specific task, such as counting basketball passes, can completely miss an unexpected person in a gorilla suit walking through the scene. The shocking part is not that their eyes failed. The image was there. The shocking part is that the brain, busy with its assignment, did not promote that information into awareness. You do not perceive everything in front of you. You perceive what your brain selects, prioritizes, and believes matters at that moment. This ability is useful because the world contains too much detail to process fully all at once. Every room is full of colors, shadows, edges, movements, sounds, body sensations, and tiny changes. And if all of it entered awareness equally, your mind would drown in its own input. So the brain filters. It suppresses the unnecessary, strengthens the relevant, and creates the feeling that you are seeing a complete world, when in truth you are seeing a managed version of it. This can help you read, drive, listen, search, and survive, but it can also make you blind to what does not match your focus. A friend's expression may change while you are thinking of what to say next. A danger on the road may be missed when your attention is locked onto your phone. A new object in a familiar room may vanish from awareness because your brain expects the old layout. This is not stupidity, and it is not weakness. It is the cost of limited attention. Your conscious mind is narrow, even when your eyes are open wide. And this should make you more humble about certainty, because saying "I would have noticed" is often a confidence your brain does not deserve. Reality can be in front of you and still remain unseen, not because it is hidden, but because your attention did not choose it. The lesson is quiet but powerful. Awareness is not a mirror. It is a selection, and sometimes the invisible thing is not behind you, not far away, not buried in darkness, but standing right in the center of your view, waiting for your mind to make room for it. Most of matter's mass comes from energy, not solid stuff. The weight of your body is not mostly the weight of tiny solid pieces, but the energy of restless fields trapped inside the heart of matter. That sounds almost impossible, because the world feels heavy in such a simple way. A stone presses into your palm. A chair holds you up. Your bones feel dense, your muscles real, the ground firm beneath your feet. It is natural to imagine matter as a collection of tiny hard ingredients stacked together, and mass as the simple sum of those ingredients. But when physicists look inside atoms, the story becomes much stranger. Most of the mass in ordinary matter comes from protons and neutrons inside atomic nuclei, and protons and neutrons are not solid little balls. They are made of quarks bound together by the strong force, surrounded by a violent dynamic sea of gluons and energy. The individual quarks themselves contribute only a small part of the proton's mass. Most of what you call mass comes from the energy of motion, tension, and interaction inside that tiny system. The strong force is so intense that the energy stored in the binding and motion of the particles becomes mass. In other words, much of the heaviness of the visible world is not resting material, but contained activity. A mountain feels still, but its mass comes from countless hidden structures where energy is locked into stable form. Your body feels like substance, but much of its mass is the result of energy behaving as if it has settled into matter. The Higgs field also plays an important role by giving fundamental particles like electrons and quarks their own masses. But for the matter you touch every day, the greater share comes from the energy inside protons and neutrons. This means solidity is not as simple as it feels. The ordinary world is not built from dead, hard beads of stuff. It is built from fields, forces, motion, and energy organized so tightly that your senses experience them as weight. And this should make the familiar world feel quietly transformed. When you lift your hand, when you feel your heartbeat, When you hold a cup, you are not only interacting with matter, you are interacting with energy made stable, energy folded into structure, energy carrying the appearance of substance. The universe did not need to make reality from solidness first. It found a deeper way. Let energy bind, let fields interact, let patterns hold, and what emerges is something heavy enough to become stars, planets, bodies, and the feeling of a world that can be touched. Your emotions can change what reality feels like. A room can become heavier without a single object inside it moving, simply because your emotional state has changed the way your brain is reading the world. This is not a weakness of character or a poetic exaggeration. It is part of how perception works. Your emotions are not floating separately from reality like music added after a film. They help shape what your brain notices, how strongly it reacts, and what meaning it gives to the signals arriving from your senses. When you feel safe, the world can seem wider, softer, easier to explore. A stranger's face may look neutral, a quiet hallway may feel peaceful, and a future problem may seem manageable. But when fear, stress, grief, or shame rises in the body, the same world can narrow around you. Your attention locks onto possible threats. Your muscles tense. Your heartbeat becomes more noticeable. Stress chemicals prepare the body for action, and the brain begins to treat uncertainty as danger. Nothing outside may have changed, yet the scene feels different because your nervous system has changed its interpretation. This is why anxiety can make an ordinary sound feel sharp, why sadness can drain color from a familiar place, why anger can make another person's words seem more hostile than they were, and why love can make a simple moment feel almost luminous. The brain does not process emotion after perception is finished. Emotion is one of the ingredients in perception itself. It guides attention, filters importance, and attaches value. Even pain can be shaped by emotion and context. The same physical sensation can feel more intense when you are afraid, exhausted, or alone, and more bearable when you feel safe, understood, or in control. Time can shift too. Fear can make seconds feel stretched, while joy can make hours disappear. Your reality is not imaginary in those moments. You are not inventing the world. You are experiencing the world through a body that is constantly measuring safety, meaning, and need. And this should make you more careful with your own certainty. When reality feels unbearable, it may not mean the entire world has become dark. It may mean your nervous system is viewing it through the weather of emotion. When everything feels possible, it may not mean all limits have vanished. It may mean your body is temporarily tuned toward openness. The lesson is not to distrust your feelings, but to understand their power. Emotions are not just reactions to reality. They are lenses through which reality becomes personal. They do not create the outside world from nothing, but they change the weight, color, distance, and meaning of everything you meet. And perhaps learning this gives you a quieter kind of freedom. Not the power to control every feeling, but the awareness to ask, is the world truly this way? Or am I seeing it through the state I am in? A quantum state can be real without being visible. Something can be physically real long before it becomes something your eyes could ever point to. A quantum state is one of the clearest examples of this strange idea, because it does not usually appear as a visible shape, color, or tiny object sitting in space. You cannot open a box, look inside an atom, and see the quantum state glowing there like a label. Yet physicists treat quantum states as deeply important because they describe what a system is capable of doing, what outcomes may appear when it is measured, and how those outcomes are connected. Think of a single electron in an atom. You do not see a little planet circling a tiny sun. What exists is better described as a state, a structured set of possibilities, energies, and allowed behaviors. That state can be real in the sense that it produces real effects, even if it is not visible in the ordinary sense. It can determine how an atom absorbs or emits light. It can shape the colors of materials, the behavior of lasers, the stability of chemistry, and the way tiny systems respond to magnetic fields. The state itself is not seen directly. It is inferred through patterns. Scientists prepare many identical systems, measure them carefully, and build up evidence from repeated results. In advanced experiments, they can even reconstruct aspects of a quantum state through a process called quantum tomography, not by photographing it like a stone, but by gathering enough measurement outcomes to reveal its hidden structure. This is important because our instincts often confuse visibility with existence. If something cannot be pictured, touched, or watched directly, the mind wants to call it less real. But physics has learned to be more patient than the senses. A magnetic field is not visible by itself, yet iron filings can reveal its pattern. Air is unseen until it moves leaves or fills your lungs. In the same way, a quantum state can be invisible while still guiding what becomes observable. The mystery is that it is not simply a secret object hiding behind a curtain. It is more like the deep condition of a system before one particular result appears. It holds the structure of what may happen, not as a vague dream, but as a precise physical description tested again and again. And perhaps this is where reality becomes more subtle than the eye expects. The visible world is not the whole world. Sometimes what matters most is not the thing you can see, but the invisible state that decides what seeing will later reveal. A quantum state reminds you that reality is not always a display. Sometimes it is a set of hidden possibilities so real that the entire visible outcome depends on them. Fields may be more real than particles. The deepest layer of matter may not be made of little things sitting in space, but of invisible fields that fill space before any particle appears. This idea quietly overturns the picture most people carry in their minds. We are taught to imagine the universe as a collection of objects. Atoms made of smaller pieces made of even smaller pieces, as if reality is a set of nested boxes waiting to be opened. But quantum field theory suggests a stranger foundation. What we call particles may be local excitations of fields, brief concentrated disturbances in something more spread out and more basic. An electron is not just a tiny bead drifting through emptiness. It can be understood as an excitation of the electron field. A photon is connected to the electromagnetic field. Other particles belong to other fields. The field is not merely a background decoration added after the particle exists. In many modern descriptions, the field is the deeper thing, and the particle is what appears when that field carries a packet of energy in a particular way. Imagine the surface of a lake. A ripple can travel across it, rise, fade, and interact with other ripples, but the ripple is not separate from the lake. It is a pattern of the lake itself. In a similar but far more precise physical sense, particles may be patterns of fields rather than independent grains of substance. This helps explain why identical particles are truly identical. Every electron has the same basic properties because each one is an excitation of the same underlying field, not a separately manufactured object with its own private material. It also helps explain why particles can be created or destroyed in high-energy interactions. The field remains, while excitations appear, transform, or vanish according to the rules of physics. The ordinary world hides this from you because fields do not feel like objects. You can hold a stone, but you cannot hold the electron field in your hand as a separate thing. Yet the stone's solidity, chemistry, color, and structure all depend on fields behaving in stable ways. Even empty space is not simply empty if fields remain in their lowest states. So perhaps particles feel more real to us only because they are the part of the field that becomes noticeable, measurable, countable. They are the visible punctuation marks in a sentence written by something deeper. Fields may be more real not because particles are fake, but because particles may be temporary expressions of fields, while the fields are the continuing medium through which the universe speaks. And once you see matter this way, reality stops looking like a pile of tiny objects and begins to feel more like music. Not notes floating alone in silence, but vibrations of an underlying system, becoming form for a moment, then returning to the quiet structure that made them possible. The universe may be built from probabilities, not certainties. The universe may not be choosing one clear answer until reality forces the question to become specific. This is the unsettling heart of quantum physics. At the smallest scales, nature often does not behave as if every detail is already fixed, waiting quietly for us to discover it. Instead, the best description we have is built from probabilities, from carefully calculated chances of what may be found when a system is measured. This does not mean the quantum world is simply random in the lazy sense, as if anything can happen for no reason. It means the rules are precise, but what they give us is not always certainty. They give us a landscape of possible outcomes, each with a certain likelihood. And when measurement happens, one outcome becomes the one we actually observe. An electron in an atom, for example, is not best imagined as a tiny planet following a known orbit. It is described by a quantum state that tells us where it is likely to be found and what energy it can have. Before measurement, the theory does not always allow us to say, with ordinary certainty, it is exactly here, doing exactly this. Instead, it says, if you look in this way, these are the possible results, and these are their probabilities. That is a very different kind of reality from the one your senses prepare you for. In everyday life, uncertainty usually means ignorance. If you do not know where your keys are, you assume they still have a definite location. Quantum uncertainty is deeper. It suggests that, in some situations, nature itself does not assign certain properties in the familiar way before interaction brings a definite result. And yet this probabilistic world is not weak or vague. It is astonishingly successful. The chemistry of atoms, the stability of matter, the behavior of lasers, the operation of microchips, and the strange patterns seen in experiments all depend on these probability rules, working with incredible precision. The visible world feels solid and definite because countless quantum possibilities average into stable patterns at human scale. But underneath that calm surface, certainty may not be the foundation. Probability may be. Reality may begin not as one finished sentence, but as a set of possible endings weighted by hidden rules, waiting for interaction to make one of them actual. And perhaps that is why quantum physics feels so humbling. It does not say the universe is meaningless. It says meaning may emerge from possibility. It says the world you trust may be the final visible result of deeper chances quietly resolving into form. Certainty, then, may be less like the ground reality stands on, and more like the footprint reality leaves after it has already stepped forward. Empty space can push tiny metal plates together. Two metal plates can be pushed together by what looks like nothing, and that is where emptiness stops feeling empty in any ordinary sense. The effect is called the Casimir effect, and it begins with a strange but real idea from quantum physics. Even a vacuum is not simply a blank absence. It has allowed patterns of electromagnetic activity, like invisible modes that can exist in empty space. Now imagine placing two extremely smooth, uncharged metal plates very close together, so close that the tiny gap between them limits which of those vacuum patterns can fit inside. Outside the plates, more patterns are possible. Inside the narrow space, fewer are allowed. This difference creates a subtle imbalance, and the result is a tiny force pushing the plates toward each other. Nothing is blowing on them. No ordinary air pressure is causing it because the effect can be studied in vacuum conditions. No hidden magnet has to pull them together. The push comes from the way quantum fields behave when boundaries restrict their possible states. It is a very small force, noticeable only at extremely short distances, but its meaning is enormous. Empty space can respond to shape. The vacuum is not just a passive container where objects sit. It can be affected by the objects placed within it. The plates change the conditions of the space between them, and the space answers with a measurable force. This does not mean we can easily extract unlimited energy from nothing, and it does not make the vacuum a magical engine. The Casimir effect is delicate, precise, and easily misunderstood, but it is powerful because it turns a philosophical idea into a laboratory fact. It shows that nothing can have structure, that absence can still carry rules, that even when particles are removed, the underlying fields do not become irrelevant. And perhaps that is why the image stays with you. Two quiet plates, almost touching, moved by the invisible grammar of empty space. The universe does not need dramatic explosions to reveal its strangeness. Sometimes it reveals itself in a force so small you could miss it, yet so deep that it changes what the word empty means forever. Your sense of now is not as sharp as it feels. The present moment feels like a clean point you are standing inside, but your brain experiences now more like a small window than a sharp line. You feel as if sight, sound, touch, thought, and movement all arrive together in one instant, perfectly synchronized. But the nervous system is quietly doing something more complicated. Different signals travel and process at different speeds. Light reaches your eyes almost instantly at human distances, but the brain still needs time to turn visual input into experience. Sound travels more slowly through air. Touch signals move through nerves at different rates depending on the type of sensation, and the brain must combine all of this into one usable moment. If it did not, reality would feel fragmented. The clap would not match the hands, the voice would not match the lips, the impact would not match the pain, and every action would arrive as scattered pieces. So the brain performs a kind of temporal stitching. It groups events that occur close together and treats them as one present experience. This is why a movie can show still images rapidly and your mind sees motion. This is why a ventriloquist can make a voice seem to come from a puppet's mouth when the timing and visual cues are convincing. This is why, in some experiments, people can be fooled about the exact order of events that happen close together in time. Your now is not a perfect timestamp. It is a constructed interval, a brief edited span where the brain decides what belongs together. And this has a strange consequence. Consciousness may always be slightly late, not in a dramatic way, but in the simple biological sense that experience takes time to assemble. You are not living inside the raw instant itself. You are living inside the brain's best organized version of what just happened. Yet this delay is not a flaw. It is what makes the world feel smooth. It gives your mind enough time to bind signals into a single scene. Enough time to connect cause and effect. Enough time to make action possible without drowning in disconnected flashes. The present feels sharp because your brain hides the stitching. It gives you a flowing moment instead of showing you the seams. And perhaps this should make now feel more mysterious than before. The moment you call immediate is already processed, balanced, and held together by the nervous system. You are not standing on a mathematical edge between past and future. You are floating inside a tiny living buffer, where the brain gathers fragments of time and turns them into the feeling of being here. Matter waves make particles behave like ripples. A particle can cross an experiment like a tiny object, yet leave behind the fingerprint of a wave, as if matter itself has learned to ripple without becoming water. This is the strange idea behind matter waves. Electrons, atoms, and even larger molecules can show wave-like behavior under the right conditions, not because they are secretly little ocean waves, but because quantum physics describes them through patterns of possibility that can spread, overlap, and interfere. In daily life, matter feels sharply located. A grain of sand is here, not there. A pebble travels along one visible path. Your hand reaches one place at a time. But when scientists send electrons through carefully designed experiments, those electrons can produce interference patterns. The same kind of pattern you would expect from waves meeting and strengthening or cancelling each other. The famous insight came from Louis de Broglie, who suggested that if light could behave like both wave and particle, perhaps matter could also have a wave-like side. Experiments later confirmed this in powerful ways. Electrons can diffract around crystals. Atoms can interfere. Even some large molecules have been shown to behave according to quantum wave rules when they are isolated carefully enough from the noisy outside world. This does not mean an electron is spread out like a visible smear you could photograph in the air. It means its quantum state carries wave-like properties, and those properties guide the chances of where the particle may be detected. When a detection finally happens, you do not see a soft ripple landing everywhere. You see a localized event, one mark, one hit. But when many particles are sent one by one through the same setup, the hidden wave-like pattern slowly appears in the statistics, as if each individual event is a single word, and the full experiment is the sentence they were always forming together. This is what makes matter waves so important. They show that the line between object and wave is not as simple as human intuition wants it to be. The solid world you trust is built from ingredients that, at small scales, do not behave like miniature versions of chairs, stones, or dust. Their behavior depends on wavelength, momentum, measurement, and interaction with the environment. And when the environment becomes too noisy, when particles bump, scatter, heat, and exchange information with their surroundings, the delicate wave-like behavior becomes hidden, and the familiar classical world returns. That is why you do not walk through a doorway like a spreading wave or interfere with yourself like an electron in a lab. Your body is far too large, warm, and constantly interacting with the world for those delicate quantum effects to remain visible. But underneath the ordinary stability of matter, the wave nature is still part of the deeper rulebook. Matter waves remind you that reality is not built from dead little dots moving through emptiness. It is built from patterns that can spread before they appear, from possibilities that can overlap before one outcome is found, from a quiet rhythm beneath substance itself. And perhaps the most humbling thought is this: the world feels made of solid things, but at its foundation, even matter carries something like a hidden music, a wave-like order that only becomes visible when the universe is quiet enough to let it sing. The Higgs field helps give particles mass. A particle can move through the universe as if it carries weight, not because it is made of tiny heaviness, but because it is constantly meeting an invisible field spread through all of space. This is the strange role of the Higgs field. Unlike a field that appears only around a magnet or near an electric charge, the Higgs field is thought to be present everywhere, even in the emptiest regions. Some fundamental particles interact with it strongly, and that interaction gives them more mass. Others interact with it weakly and remain lighter. Particles of light, photons, do not gain rest mass from the Higgs field, which is one reason light can travel through empty space at the cosmic speed limit. The important thing is that mass is not always a simple built-in substance a particle owns by itself. For many fundamental particles, mass is connected to how they relate to this invisible background field. You can think of it gently, not as particles pushing through thick syrup, because that image can be misleading, but as reality giving different particles different kinds of resistance to changes in motion depending on how they couple to the Higgs field. Without this field, electrons and quarks would not have their familiar masses. Atoms would not form the same way. Chemistry would be radically different, and the stable matter needed for stars, planets, and bodies like yours would not exist as we know it. The discovery of the Higgs boson was important because it was like finding a ripple in the Higgs field, a detectable sign that the field itself is real enough to leave evidence. But the Higgs boson is not the field itself. It is an excitation of the field, a brief appearance that reveals the deeper presence beneath it. This is what makes the idea so haunting. Something invisible, silent, and everywhere helps decide whether the basic ingredients of reality can become structured enough to build a world. Your hand, your breath, the atoms in your blood, the screen glowing in front of you, all of them depend in part on fundamental particles having the masses they do. The Higgs field does not explain every kind of mass, and it is not a magic source of all weight, but it explains a crucial piece of why many particles are not massless. So the next time matter feels solid and obvious, remember that part of its possibility comes from an unseen field filling the universe quietly, giving certain particles the inertia they need to become part of anything lasting. Reality, at its foundation, may not begin with objects at all, but with fields so quiet you never notice them, shaping what can become heavy enough to exist. A particle's identity can become blurry. A particle can lose the kind of identity that ordinary objects seem to carry. And that makes the smallest parts of reality feel less like tiny individuals and more like interchangeable appearances of the same deeper pattern. In everyday life, identity feels obvious. One coin is not another coin. One raindrop is not another raindrop. Even if two objects look exactly alike, you can imagine them having separate histories, separate positions, separate paths through the world. You can paint a mark on one, follow it across a table and say, "This is the same one as before." But quantum particles do not always allow that familiar comfort. Electrons, for example, are not just very similar to each other. As far as physics can tell, every electron has exactly the same basic properties as every other electron. The same charge, the same mass, the same kind of behavior. If two electrons trade places in a quantum system, nature may not treat that as a new distinguishable situation in the way ordinary life would. There may be no hidden labels saying which electron was first and which was second. This is not simply because our instruments are too weak to tell them apart. It appears to be part of how quantum reality works. The particles are not like numbered marbles whose labels are too small to read. They are fundamentally indistinguishable in certain conditions, and this has real consequences. The way electrons refuse to share the exact same quantum state helps build the structure of atoms, shapes the periodic table, and allows matter to have the layered complexity needed for chemistry. Without this strange blurring of identity, the familiar world would not hold together in the same way. Other particles behave differently, allowing many of them to gather into the same state, which is why quantum identity is not a philosophical decoration, but a working rule inside nature. The deeper lesson is unsettling. At the smallest scales, which one is which may not always be a meaningful question. Identity can become less like a personal tag and more like a role in a pattern. What matters is not always the individual particle as a tiny private object, but the state of the whole system and how its parts relate. This does not mean particles are unreal. It means the idea of individuality becomes softer, stranger, less human. The universe may not be built from little-named things marching separately through space. It may be built from shared states, repeated excitations, and patterns where one particle's identity can dissolve into the behavior of the whole. And perhaps that is why quantum physics feels so quietly radical. It does not only change what matter is made of, it changes what it means for anything to be itself. Reality becomes stranger the smaller you look. The smaller you look, the less reality behaves like the world your senses were trained to trust. A table seems solid, a drop of water seems smooth, your skin seems continuous, and a grain of dust seems like the smallest kind of ordinary thing. But if you keep moving inward, the familiar picture begins to break apart. The smooth surface becomes cells, fibers, crystals, molecules, atoms. The atom becomes mostly structured emptiness, with a tiny nucleus and surrounding quantum behavior that cannot be pictured like miniature planets in orbit. Go deeper still, and matter stops feeling like a collection of clear objects and starts becoming a language of fields, probabilities, charges, energies, and interactions. The strange part is not simply that things are small. The strange part is that smallness changes the rules that seem obvious at human scale. A dust particle can have a fairly definite position in ordinary life, but an electron inside an atom is not best understood as a little dot sitting in one exact place. A wall seems continuous because your body is too large to notice the enormous difference between the scale of your hand and the scale of atoms. A material seems to have one color, one texture, one hardness, but those properties come from hidden arrangements and quantum rules that decide how electrons respond to light, how atoms bond, and how molecules hold together. The world becomes stranger because your everyday categories were built for survival, not for the deepest levels of matter. Your brain learned fruit, stone, water, fire, face, danger, shelter, not wave functions, quantum states, fields, and uncertainty. So when science looks smaller, it does not merely find tinier versions of familiar things. It finds a different kind of reality beneath familiarity. At large scales, countless tiny uncertainties and interactions average together. giving you the stable world you can walk through. But underneath that stability, nature is not using the simple grammar of chairs and rocks. It is using a deeper grammar where particles can behave like waves, identity can blur, and what exists may depend on how it interacts. This does not make the ordinary world an illusion. It makes it an emergence, a calm surface formed from hidden complexity. A quiet room is still real, a hand is still real, a table is still real, but their realness is not as simple as they feel. They are the large-scale results of a world that becomes more abstract, more delicate, and more difficult to imagine the closer you examine it. And perhaps that is the most humbling lesson. Reality does not become clearer simply because you zoom in. Sometimes the closer you look, the more the universe stops resembling a thing and starts resembling a mystery that has learned how to appear solid from far away. The vacuum can have pressure. Pressure does not always need air, water, or hands pushing against a surface. Even the vacuum itself can carry a kind of pressure that changes how the universe behaves. In everyday life, pressure feels easy to understand. Air presses on your skin. Water presses against a diver. Gas inside a balloon pushes outward. So when you imagine empty space, you probably imagine the absence of pressure, a perfect stillness where nothing is there to push or pull. But modern physics makes that picture less simple. A vacuum is not just an empty container after particles are removed. It is the lowest energy condition of fields that still exist throughout space. And when fields have energy, that energy can be associated with pressure. This becomes especially important in cosmology, where the vacuum is not just a tiny laboratory idea, but a possible ingredient in the behavior of the whole universe. The mysterious effect we call dark energy is often described in the simplest model as something like energy built into space itself, with an unusual kind of pressure. Unlike ordinary pressure that might push gas outward from one place to another, vacuum pressure can act in a way that affects the expansion of space on cosmic scales. In general relativity, pressure is not merely a detail. It can contribute to gravity and influence how the universe evolves. This is why the vacuum can be part of one of the deepest questions in science. Why is the expansion of the universe accelerating? If empty space has its own energy and pressure, then emptiness is no longer just the background where cosmic history happens. It becomes part of the story. But this must be said carefully. Scientists do not yet fully understand the true nature of dark energy, and the connection between quantum vacuum energy and the observed cosmic acceleration remains one of the hardest problems in physics. The numbers we might expect from simple quantum ideas do not match the small value the universe seems to show, which creates a profound puzzle known as the cosmological constant problem. That honesty matters because the vacuum is not a magic answer. It is a mystery with measurable consequences. Still, the idea itself is astonishing. A region with no ordinary particles can have physical properties, and those properties can help shape the fate of galaxies. The silence between things may not be passive. It may carry tension, energy, and pressure so subtle that you never feel it in your hand, yet powerful enough to matter across the largest scales. So when you hear the word empty, do not picture a dead nothing. Picture a quiet physical state with rules, limits, and hidden weight. The vacuum can have pressure, and that means the universe may be influenced not only by what fills space, but by what space itself is. Your brain builds color, depth, motion, and meaning separately. Your vision feels like one smooth picture, but your brain builds it from separate pieces before you ever know you are seeing. When you open your eyes, it seems as if the world arrives whole, color attached to objects, depth stretching into space, motion flowing across the scene, and meaning appearing instantly in faces, words, roads, shadows, and gestures. But the brain does not receive a finished image. It receives streams of signals that must be processed in different ways. Some regions help analyze color, separating wavelengths of light into the reds, blues, greens, and subtle shades that make the world feel painted. Other systems compare the slightly different images from your two eyes to estimate depth, allowing a flat pattern on the retina to become a room with distance, edges, and reachable objects. Other pathways are especially sensitive to motion, helping you notice a falling cup, a moving car, a hand waving, or a shadow crossing the floor. And beyond all of that, higher parts of the brain attach meaning. This shape is a chair. That movement is a threat. That expression is sadness. That symbol is a letter. That face belongs to someone you know. The strange part is that these processes are partly separate. In certain brain injuries, a person may recognize an object's shape but struggle to see motion smoothly, as if the world appears in frozen steps. Others may lose the ability to perceive color while still seeing form. Some can see an object but fail to identify what it means. These rare cases reveal what normal vision hides. Seeing is not one single act, but a coordinated construction. Your brain binds color, depth, movement, memory, attention, and meaning into one unified experience so quickly that you mistake the result for direct reality. This binding is useful because you need a world that feels whole enough to act inside. You need to know not just that something is red, but that it is a stop sign. Not just that something is moving, but that it is approaching. Not just that a face has lines and shadows, but that it is angry, tired, kind, or familiar. Vision is therefore not merely about light. It is about interpretation layered onto light. And perhaps the most unsettling truth is that the seamless world in front of you is a kind of achievement. It is not simply given, it is assembled. Every ordinary glance is the final product of many hidden systems working together, turning scattered signals into a reality that feels whole, meaningful, and ready for you to enter. Particles can become entangled across distance. Two particles can be separated by enormous distance and still behave as if they belong to one shared fact. This is the strange power of quantum entanglement, one of the clearest places where reality refuses to act like a collection of fully separate objects. In ordinary life, distance feels like separation. If you place one coin in one room and another coin across the world, what happens to one should not instantly tell you anything deep about the other, unless someone carried a message between them. But entangled particles are different. When two particles are created or interact in certain ways, their properties can become linked so that they must be described as one combined quantum system, even if they later move far apart. When one is measured, the result is correlated with the result you would find for the other, more strongly than ordinary hidden coordination can explain. This has been tested in experiments inspired by Bell's theorem, and the results show that nature does not fit the simple picture of particles carrying pre-written instructions in a completely local way. The important detail is that entanglement does not let us send useful messages faster than light. You cannot use it like a cosmic telephone. The individual result of a measurement still appears unpredictable, and only when observers later compare their results through normal communication do the deep correlations become clear. So the mystery is not a simple violation of communication speed. The mystery is that the universe seems to preserve relationships that are not explained by ordinary distance-based thinking. The particles do not behave like two separate dice secretly programmed to match. They behave like parts of a single quantum description stretched across space. This challenges the instinct that reality is built from independent pieces first, and relationships second. In entanglement, the relationship may be more fundamental than the parts. And that is what makes it so unsettling. Space can separate the particles, but the quantum state still ties their possible outcomes together. The universe seems to say that far apart is not always the same as fully independent. This idea now matters not only for philosophy, but for real technology. Quantum computing, quantum cryptography, and quantum communication research all depend on the strange strength of entangled states. Yet beneath the technology, the emotional weight remains. Entanglement does not prove that human thoughts are magically connected across distance, and we should not pretend it does. But it does show that at the foundation of matter separateness is not as simple as it feels. The smallest systems can share a kind of physical togetherness that survives distance, reminding you that reality may be woven less like a pile of isolated things and more like a hidden pattern where relationships can remain real, even when space stretches between them. Light from distant galaxies has been stretched by space. A galaxy can send out blue-white starlight, and by the time that light reaches us, space itself may have pulled it into a deeper shade of red. This is not because the light became tired in some ordinary sense, or because it rubbed against invisible dust until it weakened like an old voice. The real idea is stranger and more elegant. While the light was traveling, the universe kept expanding, and the very wavelength of that light was stretched along with space. Light carries its color in the spacing of its waves. Shorter wavelengths appear bluer, longer wavelengths appear redder, and when space expands during the light's journey, those wavelengths can be lengthened. Astronomers call this cosmological redshift. It is one of the main clues that distant galaxies are not merely sitting in a fixed cosmic room, but are part of a universe whose large-scale distances have been growing over time. The farther away a galaxy is, the longer its light has usually been traveling, and the more expansion it has experienced along the way. By the time that light arrives at a telescope, it carries a stretched signature, like a message written on elastic paper that was pulled wider during delivery. Scientists can read this stretching by looking at patterns in the galaxy's light, especially known fingerprints from atoms, and seeing how far those patterns have shifted toward redder wavelengths. This is how redshift becomes a cosmic measuring tool. It helps astronomers estimate how much the universe has expanded since the light began its journey, and it lets us look backward into earlier chapters of cosmic history. Some of the most distant galaxies are seen not as they are now, but as they were when the universe was much younger. Their light stretched across billions of years of expansion before reaching us. This does not mean space is physically grabbing light like a hand. It means that light travels through a changing geometry, and its wavelength reflects that change. The universe leaves its history inside the light itself. Every stretched beam from a faraway galaxy is a quiet record of distance, time, and expansion written into color. So when you see an image of deep space, you are not only seeing ancient starlight, you are seeing light that has been reshaped by the growth of the cosmos, a signal that began in one era and arrived in another, carrying proof that even emptiness between galaxies has a history. The smallest things do not have clear edges. The smallest things in nature do not end with clean borders the way your hand, a stone, or the edge of a table seems to end. At human scale, edges feel obvious because your senses are built to divide the world into usable shapes. This is the cup, this is the air, this is skin, this is surface, this is empty space around it. But when you look deeply into matter, the idea of a sharp boundary begins to soften. An atom is not a tiny solid ball with a hard outer shell. Its nucleus is extremely small compared with the space around it, and its electrons are not little beads tracing neat circular paths. They are described by quantum states, spread out patterns that tell us where an electron is likely to be found and how it can behave. So where does an atom truly end? There is no simple wall. There is a region where the electron's presence becomes less and less likely, fading outward rather than stopping suddenly. The edge is more like a mist thinning into air than a brick wall ending at a line. This does not mean atoms are vague in a useless way. Their behavior is precise enough to build chemistry, crystals, DNA, metals, water, and the entire material world. But their precision is not the same as the sharpness your eyes expect. Even particles themselves can resist the idea of perfect localization. The more tightly you try to define certain properties, the more other aspects become uncertain. Not because the instruments are merely clumsy, but because quantum reality does not always offer the kind of exact boundaries classical intuition wants. At small scales, where it is, can become a question answered by probability, interaction, and measurement rather than by a tiny outline drawn in space. And the edges of ordinary objects are also less absolute than they feel. The surface of your skin and the surface of a table are made of atoms whose electron clouds repel and interact before any simple solid contact occurs. What you experience as a clean boundary is really the large-scale result of countless tiny fields and forces resisting overlap. The world becomes smooth and sharply outlined only because your brain and body operate far above the scale where the fuzziness matters. You do not see the fading probability around atoms. You see shape. You do not feel quantum softness. You feel surface. But beneath that surface, nature is not built from perfect little cutouts. It is built from zones, clouds, states, interactions, and fading possibilities. The smallest things do not have clear edges because reality, at its foundation, is less like a drawing made with hard lines, and more like a pattern that becomes definite only when the world asks it to take form. Your brain can mistake imagination for experience. Your brain can rehearse something so vividly that your body begins to treat it less like a thought and more like something that happened. This is one of the quiet reasons imagination is powerful and sometimes dangerous. When you picture a future conversation, replay an argument that never fully occurred, imagine falling, failing, being watched, being loved, being abandoned, or being safe. Your brain is not doing nothing. Many of the same networks used for perception, emotion, movement planning, and memory can become active during imagination. The scene may not be happening outside you, but inside the nervous system it can still produce real signals. A faster heartbeat, tense muscles, warmth in the face, fear in the stomach, comfort in the chest, or tears from an event that exists only in the mind. This does not mean imagination and reality are identical, and it does not mean the brain is foolish. It means the brain is built to simulate. Simulation helps you prepare before danger arrives, practice before action, predict social situations, and learn from possibilities without needing to live them all physically. Athletes use mental rehearsal because imagining a movement can strengthen the brain's preparation for doing it. Therapists use imagery because imagined safety, exposure, or reframing can influence emotional response. But the same gift can turn against you. Anxiety often works by making imagined threats feel physically present. A person may suffer from a future that has not happened, a rejection that has not been spoken, or a disaster that exists only as a mental movie. The body reacts because the brain is not asking only, "Is this outside me?" It is also asking, "Is this important, vivid, and emotionally charged?" Memory can blur with imagination too. If you imagine an event repeatedly, especially with detail and emotion, the mind may later treat parts of it as familiar, and familiarity can be mistaken for truth. This is one reason false memories can feel sincere. People are not always lying when they remember incorrectly. Sometimes the brain has woven imagined details into the fabric of remembered experience. The boundary between lived, remembered, feared, and imagined is not a solid wall. It is a living border managed by attention, emotion, and belief. And this should make you careful with the stories you repeat inside yourself. Your imagination is not fake just because it is internal. It can train your nervous system, shape your expectations, color your memories, and prepare your body for worlds that may never arrive. The lesson is not to fear imagination, but to respect it. Inside your mind, a thought can become a rehearsal. A rehearsal can become a feeling, and a feeling can begin to look like reality before reality has even spoken. The vacuum can change the energy of atoms. An atom is not surrounded by perfect emptiness. Even the quiet vacuum around it can slightly change what the atom is allowed to become. This sounds almost impossible at first, because an atom already feels like one of the smallest complete things in nature. A tiny system with its own electrons, its own nucleus, its own internal rules. But in quantum physics, an atom does not live in isolation from the background of fields around it. Even when ordinary particles are removed and space is as empty as we can make it, the electromagnetic field still has a lowest possible quantum state and that state is not the same as a dead absence. It can subtly interact with the charged particles inside atoms, especially electrons, and shift their energy levels by extremely tiny amounts. One famous example is the Lamb shift, discovered when physicists measured hydrogen with such precision that they found a small difference between energy levels that earlier theory had expected to be the same. This tiny mismatch became a clue that the vacuum itself was participating, not in a dramatic way, not like a storm shaking the atom, but like a quiet background presence changing the exact conditions under which the electron exists. The electron is influenced by its own interaction with the surrounding quantum field, and the result is a measurable shift in atomic energy. That may sound small, but small does not mean unimportant. These tiny corrections helped confirm that the vacuum is physically meaningful, and that quantum electrodynamics, one of the most precise theories in science, describes nature with astonishing accuracy. The lesson is subtle. An atom's energy is not determined only by the obvious ingredients inside it. It is also shaped by the invisible field environment in which it lives. What we call empty space can leave fingerprints on matter so delicate that only careful experiments reveal them. Yet those fingerprints are real. This does not mean atoms are unstable because of the vacuum, and it does not mean empty space is violently boiling in the everyday sense. It means the boundary between thing and background is not as clean as it feels. The atom and the vacuum belong to the same, deeper physical story. So when you imagine matter floating in emptiness, remember that the emptiness is not merely around matter like a blank room around furniture. It can help define the exact energies matter can have. Even the simplest atom carries a whisper of the vacuum, a reminder that reality is shaped not only by what is present, but also by the quiet fields that remain when everything visible is gone. Cause and effect can become hard to order in quantum physics. Cause and effect feel like the strongest grammar of reality, but in quantum physics that grammar can become harder to read than your everyday mind expects. In ordinary life, one thing happens, then another follows. A match is struck, then the flame appears. A glass falls, then it breaks. A message is sent, then it is received. This order feels so natural that it becomes almost invisible, like the floor beneath thought itself. But at the smallest scales, especially in carefully designed quantum experiments, the sequence of events can become less straightforward. This does not mean the universe becomes meaningless or that causes disappear completely. It means that the clean order we expect from ordinary experience may not always be fundamental in the same simple way. In some quantum situations, a system can be placed in a state where different possible sequences must be considered together before a final result is observed. Researchers studying ideas like indefinite causal order explore whether, under certain conditions, it may not be correct to say that event A definitely happened before event B, or event B definitely happened before event A. Instead, the order itself can behave like part of the quantum structure, not something fixed from the outside in advance. One experimental example uses quantum switches, where the order of two operations can be put into a kind of controlled quantum arrangement, allowing processes to be combined in ways that have no ordinary classical equivalent. This is not time travel in the fantasy sense, and it does not let you send a message into yesterday. It is subtler than that. It shows that when systems are small enough and isolated enough, nature may allow relationships between events to be described in ways that resist a single fixed timeline until the process is completed and measured. The deeper point is that before and after may not always be as simple as human instinct assumes. At our scale, cause and effect become stable because countless interactions with the environment lock events into a clear order. The world of falling cups, spoken words, clocks, and memories works because the quantum strangeness is hidden beneath layers of ordinary interaction. But beneath that stable surface, physics is beginning to ask whether causal order itself might sometimes be a feature that emerges, rather than a rule that is always sharply written at the foundation. And that should make reality feel both stranger and more delicate. The universe may not be a perfectly pre-sorted chain of events from beginning to end. It may be a deeper network of possible relations, where order becomes clear only under the right conditions. Cause and effect still guide the world you live in, but quantum physics whispers that, at the smallest scales, even the question, which came first, may not always have the simple answer your mind is waiting for. Space is not a passive background. Space feels empty because your body was not built to notice what space is doing. You walk through a room and treat the space between the walls as a blank allowance, a silent permission for objects to exist and bodies to move. A planet crosses space, a beam of light travels through space, a galaxy hangs in space, and the word begins to sound like nothing more than a container. But modern physics has steadily taken that simple picture apart. Space is not merely the background behind reality, it can participate in reality. In Einstein's theory, space and time are joined into a flexible structure that can be shaped by matter and energy. A massive object does not simply sit inside space like a marble in a box. It changes the geometry around it, affecting how other objects move and how light travels. This is why starlight can bend near the sun, why the path of planets is not just motion through emptiness, and why gravitational waves can pass across the universe like ripples in the fabric of space-time after massive objects collide. Space can stretch, curve, carry waves, and influence the future paths of matter. That is already far from passive. But the story becomes even stranger when quantum physics enters. What we call empty space can still contain fields in their lowest states. It can have conditions, structure, and measurable effects. The vacuum is not a dead stage after the actors leave. It is more like the quiet condition from which certain actors can appear and within which their behavior is shaped. Space also matters in cosmology. The large-scale expansion of the universe is not simply galaxies moving through a fixed emptiness. It is the growth of distances within space itself. The arena changes while the story unfolds. This means space is not just where things happen. It helps decide how things can happen, how far signals can travel, how gravity behaves, how light is stretched, and how the universe evolves over time. The old image of space as a dark, silent box is comforting but too simple. A better image is something quieter and deeper. Space as part of the physical system, not outside it. Not a painted background, but a living geometry with rules of its own. You do not feel this when you cross a room because the effects are usually too subtle at human scale. The floor seems still, the air seems ordinary, and distance seems obvious. But beneath that ordinary calm, space is not doing nothing. It is holding relationships, allowing motion, responding to mass, carrying fields, stretching across cosmic time, and giving reality the structure in which matter can become a world. Perhaps the most unsettling lesson is that the emptiness around you is not an absence from the universe. It is one of the universe's most important ingredients. Reality may depend on interaction more than objects. Reality may not be built from lonely things first, but from what happens when things meet. This idea quietly changes the whole picture of existence, because your mind naturally wants to start with objects, a particle here, an atom there, a body, a planet, a star, each one carrying its own fixed identity before it ever touches anything else. But modern physics often suggests a more relational world. A particle becomes meaningful through interaction. It is detected when it leaves a mark, changes a field, transfers energy, scatters from something, or becomes part of a larger system. An electron's charge is not just a private label hidden inside it. It is known through how the electron responds to electromagnetic fields and how other charged things respond to it. A photon is not experienced as a tiny glowing bead floating by itself. It is known when it is emitted, absorbed, reflected, or registered by matter. Even mass, energy, position, and motion are not always best understood as isolated possessions, but as features revealed through relationships, measurements, and changes. This does not mean objects are fake, or that nothing exists unless a human looks at it. That would be too simple and misleading. The deeper point is that the physical world may not be a collection of sealed-off pieces that later begin to interact. It may be a network of interactions from which the familiar idea of separate pieces becomes useful only at larger scales. In quantum physics, especially, a system's properties can depend on how it is prepared, how it is measured, and what it has interacted with. In field theory, particles can appear as excitations that gain their identity through the field they belong to and the interactions they can have. In chemistry, an atom's meaning changes depending on its bonds. Carbon in diamond is not the same lived reality as carbon in graphite, not because carbon stopped being carbon, but because its relationships changed the structure it could become. In biology, a single molecule may do nothing important alone, yet inside a cell, surrounded by partners, signals, membranes, and timing, it becomes part of life. This pattern repeats everywhere. Things are defined not only by what they are, but by what they can do, what they can affect, what can affect them, and what larger order they help create. Your own body is not a pile of independent parts. It is breathing, signaling, exchanging, repairing, sensing, and responding. Your mind is not a single object hidden inside the skull, but an ongoing coordination of brain, body, memory, environment, and attention. Reality becomes less like a museum of separate objects and more like a conversation that never stops. The table, the star, the atom, the cell, the thought. Each feels like a thing because interactions have become stable enough to hold a recognizable form. But beneath that stability, existence may be relational before it is object-like. Something is real not only because it sits somewhere, but because it can participate. It can leave traces, it can change and be changed. And perhaps that is the quiet lesson. The universe may not begin with isolated nouns, but with verbs. Not with things alone, but with meeting, exchanging, responding, binding, scattering, and becoming. What you call an object may be what interaction looks like when it lasts long enough for the mind to give it a name. Virtual particles are not ordinary particles. Virtual particles are strange because their name makes them sound like tiny objects briefly appearing in empty space, when in reality they are not ordinary particles at all. A real particle is something that can, in principle, be detected as an actual outcome. A photon absorbed by a sensor, an electron leaving a track, a particle striking a detector and depositing energy. Virtual particles are different. They are not little invisible marbles secretly flying around, waiting to be caught. In quantum field theory, they appear inside calculations as temporary internal links between interactions, mathematical pieces that help physicists describe how fields influence one another. They are called virtual because they do not have to obey the same relationship between energy, momentum, and mass that real, detectable particles obey. You cannot place a virtual particle in a box, wait for it to arrive, and measure it like an ordinary object. It is not a free traveler in the world. It is part of the hidden accounting of an interaction. When physicists draw Feynman diagrams, the real particles are the incoming and outgoing lines, the things that can be prepared or detected. The virtual particles are the internal lines, the unseen structure of the calculation that helps connect what goes in with what comes out. This is why popular language can mislead. Saying that particles borrow energy or pop in and out of existence can create a vivid image, but it can also make the vacuum sound like a swarm of tiny ghosts. The more careful truth is less cartoonish and more profound. Quantum fields can have fluctuations and interactions that are not directly visible as ordinary particles, yet their effects show up in extremely precise measurements. For example, the magnetic behavior of the electron has been predicted and measured with astonishing accuracy by including these virtual contributions in the theory. That does not mean virtual particles are fake in a useless sense. It means they are not real in the same way a detected photon or electron is real. They are part of the machinery by which the theory describes how reality transforms between observable states. This distinction matters because it teaches you how subtle physics becomes when language tries to follow it. The word particle no longer always means a tiny thing you could point to. Sometimes it means a detectable excitation. Sometimes it means an internal feature of a calculation. Sometimes it is a way of tracking how fields exchange influence without pretending that every symbol in the math is a miniature object in space. And maybe that is the deeper lesson hidden inside virtual particles. Reality is not always made of things that can be pictured. Some of its most powerful ingredients are not objects, but processes, constraints, relationships, and invisible contributions that only reveal themselves through what they allow the real, measurable world to do. Dark energy may be stretching the universe apart. Dark energy is strange because it does not pull galaxies together like gravity. It seems to make the distance between the farthest ones grow faster with time. For most of human history, if people imagined the universe changing, they imagined gravity as the great cosmic hand, slowly gathering matter, slowing motion, pulling stars, galaxies, and clusters toward one another. Even after scientists learned that the universe was expanding, many expected that expansion to gradually slow down, because gravity from all the matter in the cosmos should resist it. But in the late 20th century, observations of distant exploding stars revealed something deeply unexpected. The expansion of the universe appears to be accelerating. Space is not merely growing. On the larger scales, its growth seems to be speeding up. To describe whatever is causing this, scientists use the name dark energy. The name sounds dramatic, but it is really a placeholder for a mystery. It does not mean we understand it. It means the evidence points to something in the universe's behavior that ordinary matter and gravity alone do not explain. In the simplest current model, dark energy acts like an energy associated with space itself, nearly uniform and persistent as the universe expands. If that picture is right, then as space grows, there is more space carrying this strange effect, and the expansion continues to accelerate. This is not like an explosion pushing galaxies through a pre-existing emptiness. It is subtler. The distance between distant galaxy groups increases because the fabric of space between them changes. Nearby systems like our solar system, our galaxy, and gravitationally bound galaxy groups do not get torn apart by today's dark energy because local gravity and other forces are far stronger on those scales. The stretching matters most across immense cosmic distances where galaxies are not tightly bound to each other. Over billions of years, this can make the universe increasingly lonely. Distant galaxies may drift beyond our ability to ever reach or communicate with them, and their light may become stretched, dimmed, and harder to detect. The future sky could slowly lose much of the distant cosmic story that is still visible to us now. And yet dark energy is not simply a force of destruction. It is a clue that empty space may have properties we do not fully understand. It asks whether the vacuum is truly quiet, whether the structure of space-time has a built-in tendency, whether our theory of gravity is complete on the larger scales, or whether something deeper is missing from our picture. Scientists continue to test these possibilities by measuring supernovae, galaxy distributions, gravitational lensing, and the ancient afterglow of the early universe. The answers are not finished, and that uncertainty is part of the honesty. What we know is powerful enough. The larger scale future of the cosmos may depend on something we cannot see, touch, bottle, or explain in ordinary language. Dark energy may be stretching the universe apart, not violently, not loudly, but with a patient pressure written into the growth of space itself. And perhaps that is what makes it so haunting. The end of the universe may not arrive as fire, collapse, or a sudden tear, but as distance becoming deeper than connection, as galaxies fading from one another's skies, as reality slowly spreading its own contents so far apart that the cosmos becomes quieter, colder, and harder to know. Your inner world is private and cannot be directly shared. No one has ever stepped inside your experience, not even the people who know your voice, your face, your habits, and your history better than anyone else. They can sit beside you, listen to you, watch your expression change, hold your hand when you are afraid, and still never feel the exact private texture of what it is like to be you from the inside. This is one of the deepest truths about consciousness. Your inner world is not directly shareable. You can describe it, point toward it, compare it with memories, turn it into language, art, music, tears, silence, or a trembling sentence, but the experience itself remains yours. When you see the color blue, another person may agree that the sky is blue, may name the same wavelength range, may show similar brain activity, and may use the same word with confidence, but you cannot open a door between minds and hand them the raw feeling of your blue. When you feel grief, someone may understand the situation, remember their own losses, and respond with real compassion, but they are still building a version of your pain inside their own nervous system. Empathy is powerful, but it is not teleportation. Language is beautiful, but it is not direct transfer. Even modern brain scans, as impressive as they are, do not reveal experience itself. They show patterns of blood flow, electrical activity, connectivity, and neural response. They can tell us that parts of the brain are active during pain, memory, fear, attention, or imagination. But they do not display the living feeling the way a screen displays a photograph. A scientist might map the brain while someone listens to music, yet the map is not the music as it is heard from within. This is why consciousness remains so difficult to explain. The outside view and the inside view are not the same kind of thing. From the outside, you are a body, a brain, a voice, a pattern of behavior, a biological system responding to the world. From the inside, you are warmth, pressure, longing, color, memory, doubt, meaning, and the strange, quiet sense of being here. Other people can infer that inner world from your words and actions, just as you infer theirs, but inference is not entry. And still, this privacy is not only loneliness, it is also what makes each conscious life precious. Your inner world is a place no one else can fully occupy, a private weather shaped by your body, your memories, your fears, your language, your attention, your dreams, and the countless moments that have taught your brain what the world means. You can never fully export it, but you can express it. You can build bridges from it. You can let someone come close enough to recognize the outline, even if they never touch the center. And perhaps that is what human connection truly is. Not two minds becoming one, but two private worlds reaching across the gap with enough honesty to say, I cannot be inside you, but I believe there is something there. The universe may be more like a process than a thing. The universe may not be a finished object sitting in existence, but an ongoing activity that never stops becoming itself. This is difficult to feel because your senses prefer nouns. They show you stars, stones, oceans, bodies, tables, galaxies, and call them things, as if each one were a stable piece of reality with clear borders and a fixed identity. But when you look more deeply, almost everything you call a thing is really a process holding its shape for a while. A star is not a glowing object in the simple sense. It is a balance of gravity, pulling inward, and nuclear reactions pushing outward. A long-burning transformation of matter into light. A river is not the same water from moment to moment. It is a pattern of flow that keeps its name while its contents pass through. A living body is not a static possession. It is metabolism, repair, circulation, breathing, sensing, remembering, and constant exchange with the world. Even a rock, which feels like the symbol of stillness, is made of atoms vibrating, bonds holding, surfaces weathering, and a history of pressure, cooling, erosion, and time. The thing is what your mind sees when the process is stable enough to recognize. Physics pushes this idea even further. Matter can be described through fields, interactions, energy transfers, and changing states. The universe is not simply a warehouse containing objects. It is a web of events, transformations, and relationships that produce objects as temporary patterns. What you call a galaxy is a slow choreography of stars, gas, gravity, dark matter, collisions, births, deaths, and motion across enormous time. What you call empty space may still have fields, structure, expansion, and physical conditions. Even time itself is not just a background clock placed outside everything. It is woven into how change is measured and how events relate. This does not mean nothing is real. It means reality may be more verb than noun. A candle flame is real, but you cannot freeze it into a single piece and still have the flame. Its identity is in the burning. A song is real, but it exists through unfolding, not as one silent note. In the same way, the universe may be real as process, not a block of finished stuff, but a continuing pattern of becoming. And perhaps this changes how you see yourself too. You are not one solid self sealed inside skin. You are a continuity of breath, memory, chemistry, attention, emotion, and response. You remain you, not because nothing changes, but because change is organized enough to carry a recognizable story forward. Maybe the deepest truth is not that the universe contains processes. Maybe the universe is process, and objects are what process looks like when it slows down enough for consciousness to give it a name. Absolute nothing may be physically impossible. Absolute nothing may be the hardest idea your mind can imagine, because the moment you try to picture it, you have already made it into something. You might think of darkness, silence, empty space, a blank room, a black void with no stars inside it, but all of those are still not absolute nothing. Darkness is still a condition where light is absent. Silence is still a condition where sound is absent. Empty space is still space, with distance, geometry, physical laws, and in modern physics, fields that can remain even when ordinary particles are removed. Absolute nothing would mean no space, no time, no fields, no energy, no laws, no possibilities, no background, no observer, no place where absence could be located. And that is where the idea begins to collapse under its own weight. In physics, we can study vacuums, low-energy states, empty regions, and the behavior of fields when particles are gone. But those are still something in a physical sense. They have structure. They can be described. They can affect matter. They belong to a universe with rules. Absolute nothing, by contrast, would not simply be an empty box. It would be no box, no outside, no inside, no before, no after, no condition waiting to change. This is why some philosophers and physicists treat nothing with extreme caution. The nothing of everyday language is usually just absence relative to expectation. No water in the glass, no person in the room, no sound in the air. But the deepest nothing is not merely an empty version of the familiar world. It is the removal of the framework that makes empty meaningful at all. When cosmologists discuss the origin of the universe, this distinction becomes crucial. Even if a model describes the universe emerging from a quantum vacuum, that vacuum is not absolute nothing. It is a physical state with rules and potential. Even if time itself began with the universe, asking what happened before may be like asking what is north of the North Pole. The question uses a concept beyond the place where that concept works. This does not mean science has solved why there is something rather than nothing. It means the question is more delicate than it first sounds. Maybe absolute nothing is not a real physical option. Maybe once there are laws, fields, possibilities, or a quantum state, we are already past nothing. And if there are no laws or possibilities at all, then there is not even a meaningful way for something to begin. That is the strange trap. Nothing seems simple, but it may be too empty to do anything, too empty even to be called a state. The universe may not have emerged from nothing, in the way our imagination pictures a blank darkness suddenly producing stars. It may have emerged from a deeper condition we do not yet fully understand, one that is not ordinary space, but also not absolute absence. And perhaps that is the quiet lesson hidden here. Reality may be mysterious, not because something came from nothing, but because true nothing may not be the kind of thing reality can ever contain. The absence you imagine is already a shadow cast by existence. The future of the universe may depend on empty space. The fate of everything may not be decided by stars, galaxies, or black holes, but by the quiet condition of the emptiness between them. This is what makes empty space so strange in modern physics. It is not merely the leftover gap after matter is removed. It may have properties of its own, and those properties may influence how the entire universe ages. When people imagine the cosmic future, they often picture visible things first. Stars burning out, planets freezing, black holes swallowing matter, galaxies drifting through darkness. But the largest question may be deeper than all of that. What is the vacuum itself like? Is the energy associated with space constant? Can it change? Does it remain stable forever? Or does it belong to a state that only looks permanent because we have never seen it shift? The most familiar clue is cosmic acceleration. Observations suggest that the expansion of the universe is speeding up, and the simplest explanation is that empty space carries a small but persistent kind of energy, often linked to what we call dark energy. If that energy stays roughly the same over cosmic time, the universe may continue expanding faster and faster on the largest scales. Distant galaxies would fade beyond reach, new stars would eventually become rare, and the cosmos would move toward a colder, emptier future, where matter becomes increasingly isolated. But if the properties of empty space are not constant, the story could be different. A changing form of dark energy might alter the expansion rate. It could weaken, strengthen, or behave in ways our current measurements have not yet revealed clearly. Even the stability of the vacuum matters. In quantum field theory, a vacuum is not just nothing, but a lowest energy condition of fields. If our vacuum is the true lowest state, then the universe may remain in this condition indefinitely. If it is only a long-lived state that appears stable, then in principle, the laws and particle properties we know could depend on a deeper field condition that might not be absolutely final. Scientists study these possibilities carefully, not because they expect dramatic change tomorrow, but because the entire history and destiny of the cosmos may depend on what empty space fundamentally is. This is the unsettling beauty of it. The future may be written not only in the life cycles of stars, but in the silent background that surrounds every star. Space may decide whether galaxies keep drifting apart, whether the universe cools into vast isolation, whether expansion changes character, or whether the laws we call permanent are tied to a deeper vacuum state. So when you imagine the far future, do not picture only dying light. Picture the emptiness itself as an active part of the story, quiet enough to seem like nothing, yet important enough that the destiny of reality may rest in its hidden condition. Your brain creates the feeling of a single, continuous self. You feel like one continuous person because your brain keeps stitching change into a story that does not fall apart. Every morning, you wake up with the quiet assumption that the you opening your eyes is the same you who went to sleep. The same one who remembers childhood fragments, recognizes a familiar face in the mirror, prefers certain songs, fears certain losses, carries certain hopes, and moves through the world with a name that seems to belong to something stable. But the self is not a single object hidden somewhere inside the skull. There is no tiny captain sitting behind your eyes, watching everything and pulling the levers. What you call me is built from many systems working together. Memory, body sensation, emotion, attention, language, prediction, habit, and the brain's constant mapping of where your body ends and the outside world begins. Your sense of self depends partly on autobiographical memory, the collection of personal events your brain uses to say, "This happened to me." It depends on body ownership, the feeling that this hand is your hand, this breath is your breath, this pain is your pain. It depends on interoception, the brain's reading of internal signals like heartbeat, hunger, tension, warmth, nausea, and calm. It depends on social memory too, because part of who you feel yourself to be is shaped by how others have seen you, named you, loved you, rejected you, or reflected you back. The strange part is that all of this is constantly changing, yet the brain smooths it into continuity. You are not exactly the same in anger as you are in peace. You are not the same when exhausted, in love, afraid, confident, ashamed, or safe. Different memories become easier to access in different moods. Different parts of your personality rise depending on the situation. Even your body map can be altered by experiments, illusions, injury, or tools you use long enough that the brain begins to treat them as extensions of action. And still, through all this movement, the mind creates a central thread. It says, "I am the one experiencing this." That thread is useful. Without it, life would feel fragmented, impossible to organize. You need a self to make plans, take responsibility, protect the body, learn from mistakes, care about the future, and understand the past as your own. But usefulness is not the same as simplicity. The self is more like a melody than a stone. A melody remains recognizable even though each note vanishes as the next one arrives. In the same way, you remain yourself through a pattern of continuity, not through perfect sameness. Your brain edits gaps, links moments, gives your body a center, and turns scattered experience into a life that feels owned from within. This does not make the self fake. It makes it constructed, maintained, and alive. You are not an illusion in the sense of being nothing. You are a process that feels like a person because the brain is constantly organizing experience around a point of view. And perhaps that is the quiet wonder of being human. The I you feel so directly is not a fixed jewel buried inside you, but a living story the nervous system keeps renewing, moment by moment. So change can feel like continuity and a moving life can still say, "This is me." Some quantum histories are not definite until measured. The past feels finished only because the world you live in is too large, too noisy, and too settled to show you how strange history can become at the quantum scale. In everyday life, history seems like a fixed chain. A stone fell, a glass broke, a door closed, a message was sent, a footprint was left behind. You may not know every detail, but you assume those details were definite all along. Something happened one way, not another. But in quantum physics, some experiments force us to be more careful with that assumption. A tiny system may not have one clear classical history before it is measured. Instead, the correct description can involve several possible histories contributing together to the final outcome. This does not mean the past is imaginary, and it does not mean your childhood or yesterday's breakfast can suddenly rewrite itself because someone looks later. The ordinary past becomes stable because huge numbers of particles interact with their environment, leaving records everywhere. Light scatters, heat spreads, memories form, marks remain. But in carefully isolated quantum systems, where the environment has not yet locked the possibilities into one ordinary story, the question, "What path did it really take?" may not have the simple answer your intuition wants. In the double-slit experiment, for example, if there is no measurement revealing which slit a particle went through, the particle's behavior cannot be explained by saying it simply chose one slit in the usual way. The final pattern depends on the fact that the alternatives were allowed to remain connected, as if multiple possible histories had to be considered together. But if you measure which path it took, the pattern changes, and the system behaves as though one history has become definite. The measurement does not merely uncover a tiny pre-written diary. It helps create the kind of record that lets a single history be spoken about. This is why some physicists use the language of histories carefully. At quantum scales, what counts as a definite past can depend on what information exists and what interactions have occurred. The deeper lesson is not that reality is chaos, but that definiteness may be something that emerges when possibilities become recorded. A history becomes solid when the universe leaves enough traces to make it irreversible in practice. Before that, nature may preserve a delicate openness that everyday experience hides from you. And perhaps this is what makes the idea so haunting. Reality may not always begin as a finished storyline waiting for observers to read it. Sometimes it may begin as a set of possible ways things could have happened, with the final record deciding which kind of past can be meaningfully claimed. The world you know is full of facts because it is full of traces, but beneath that familiar world, quantum physics suggests that history itself may sometimes need an interaction before it can harden into something we call what really happened. Reality, may not be made of things, but fields in motion. Reality may not be a universe of tiny things moving through empty space, but a universe of fields moving, changing, and briefly forming the things we mistake for final objects. This idea is difficult because your senses are trained to believe in solid nouns. You see a stone, a hand, a flame, a star, a speck of dust, and each one feels like a separate piece of existence. But modern physics often points toward a deeper picture in which what we call things are stable patterns inside something more continuous. A field is not simply a mysterious mist or an invisible fluid hiding behind matter. In physics, a field is a physical structure spread across space, carrying values and possibilities at every location, able to change, vibrate, transfer energy, and interact with other fields. What appears as a particle may be a localized excitation, a concentrated disturbance in a field, like a note rising from a string rather than a pebble placed on a table. The note is real, you can hear it, measure it, feel its effect, but it is not separate from the vibrating system that produced it. In the same way, particles may be real appearances of deeper field activity, not independent little beads with permanent private substance. And once you take this seriously, the ordinary world begins to look less like a collection of objects and more like organized motion. A beam of light is an electromagnetic field changing and traveling. The matter in your body depends on electron fields, quark fields, gluon fields, and the rules by which their excitations bind into atoms. Even what feels still is not truly still. A quiet piece of metal holds together because fields and forces maintain its structure. A cold stone rests in your hand, but inside it are vibrating atoms, quantum states, electromagnetic interactions, and stored energy arranged so steadily that your senses call it solid. The stillness is a surface impression. Beneath it, reality is activity holding form. This does not mean the world is fake, or that objects are illusions with no meaning. It means objects may be the large-scale names we give to patterns that last long enough to matter. A whirlpool is real, though it is made of moving water. A flame is real, though it is a process of chemical transformation. A song is real, though it exists only as vibration unfolding through time. Matter may be similar at a deeper level. Not dead substance first, but motion organized into persistence. Fields can be calm or excited, uniform or disturbed, stable or changing, and from their behavior come particles, forces, radiation, atoms, chemistry, stars, and eventually observers wondering what reality is made of. The phrase fields in motion matters because it shifts the question from what tiny objects are hidden underneath everything to what underlying activity gives rise to the appearance of objects at all. Maybe the universe is not a warehouse filled with little building blocks. Maybe it is more like a vast, lawful performance in which fields continuously transform, and the things we know are the recognizable shapes this transformation takes. You are not outside that performance. Your body, your thoughts, your breath, your eyes reading these words. All of it depends on field activity organized into life. And perhaps this is the quietest revolution in the idea of matter. Reality may not be made of things that move, but of movement that becomes things. The flow of time may be something we add later. Time may not be flowing around you like a river. The flow may be something your mind adds to a universe made of events. This is one of the most unsettling ideas in modern physics and consciousness, because nothing feels more obvious than time moving. You feel the present sliding forward. You feel yesterday falling behind you. You feel tomorrow waiting ahead, unopened. But when physicists describe the universe, especially through relativity, they do not always find a cosmic current carrying all things from past to future in one universal motion. They find events, a star exploding, a signal arriving, a heart beating, a photon reaching an eye, each located within space-time, each connected to others by relationships. In Einstein's picture, there is no single master clock ticking out the same now for the entire cosmos. Two observers, moving differently, can disagree about which distant events are simultaneous, and neither has to be wrong. That means the present is not a universal slice shared by everything at once. It is local, relational, tied to motion, position, and observation. The universe may contain the pattern of events, but the sensation that one bright edge of reality is sweeping across them may come from how conscious beings experience change. Your brain does not receive the whole universe. It receives signals, stores memories, compares what just happened with what is happening, predicts what may happen next, and then turns this chain into the feeling of flow. Memory is crucial here. You feel time moving, partly because you carry records of earlier states but not later ones. You remember breakfast, not tomorrow's conversation. You see a cup fall and break, but you do not see shattered pieces leap back into a cup. The world gives your brain traces, and your brain organizes those traces into a direction. Physics gives us reasons why the future differs from the past in practice. Energy disperses, records form, irreversible processes build the arrow we live by, but the smooth inner feeling of time passing is not the same thing as that physical arrow. It is an experience built by a nervous system trying to make change usable. A clock does not feel time flowing. A photograph does not feel stuck in the past. A planet does not mourn yesterday, but a mind gathers moments, links them, names one before and one after, and experiences the link as movement. This does not mean time is fake. Change is real. Aging is real. Clocks work. Causes leave effects. The universe has structure across time. But the flowing quality, the intimate sense that you are riding a moving present, may be less like an external substance and more like the way consciousness reads a sequence it cannot hold all at once. Imagine a film reel. All the frames can exist as a structure, but the movie appears only when frames are experienced in order. Your mind may be doing something similar with reality, turning relations between events into a lived current. And perhaps that is why time feels so personal. Physics may describe when events happen, how clocks compare, and how systems change. But only a conscious creature feels the ache of waiting, the softness of memory, the pressure of urgency, the sadness of a moment becoming unreachable. The flow of time may be something we add later, not as a lie, but as a translation. The universe as you see it may be a user interface. The world you see may be less like reality itself and more like a control panel your brain uses to survive reality. This does not mean the universe is fake, or that mountains, bodies, trees, and stars are meaningless illusions. It means the version of the universe that appears in your awareness may be a simplified interface, much like the icons on a computer screen. When you see a folder icon, you do not think the actual information inside the computer is a tiny yellow folder living behind the glass. The icon is useful because it hides the deeper complexity and gives you something simple enough to act on. Your perception may work in a similar way. The colors you see, the solid shapes you trust, the feeling of objects being separate and stable, the sense that space opens around you in a clean visual scene. All of this may be your nervous system's practical way of representing a world too detailed, too fast, and too complex to experience directly. Evolution did not need your ancestors to see objective truth in its deepest form. It needed them to notice food, danger, shelter, faces, movement, distance, and opportunity quickly enough to stay alive. A creature that sees a useful shortcut may survive better than a creature overwhelmed by perfect detail. So your brain gives you a world made of manageable symbols. Red can mean ripe fruit or warning. Sharp edges can mean danger. Familiar faces can mean safety or memory. Movement in the corner of the eye can demand attention before you even understand what moved. The interface is not random. It is anchored to real causes in the world. But it is not the thing itself. A color is not painted onto the object in the way it appears to you. It is your brain's way of interpreting light. A sound is not floating fully formed in space. It is your brain's interpretation of vibration. A solid object is not solid in the simple way it feels. It is a stable pattern of matter and forces that your body can interact with. The interface works because it lets you act. You can pick up a cup without knowing the quantum behavior of its atoms. You can cross a street without calculating every photon entering your eyes. You can recognize a friend in half a second without analyzing every curve of the face. That is the genius of the interface. It hides almost everything and shows you what matters for action. But the danger is that you mistake usefulness for completeness. You begin to believe that icons are the whole machine. You think the world as it appears is the world as it is. Science keeps breaking that comfort by showing that the deeper layers do not look like the interface at all. Beneath color are wavelengths and neural processing. Beneath solidity are fields, atoms, forces, and empty structure. Beneath the smooth present is delayed biological assembly. Beneath the feeling of direct contact are interactions too small to feel individually. The universe as you see it may be a user interface, not because your life is unreal, but because experience is a survival-shaped translation. And perhaps this should make reality feel more mysterious, not less. You are not trapped in a lie. You are living through a brilliant simplification, a living display built by the brain so that something as fragile as a human body can move through something as enormous as the universe and still know where to place its next step. Quantum mechanics predicts reality without explaining why it exists. Quantum mechanics can tell you what the world will probably do with astonishing accuracy, yet it stays almost silent about why there is a world doing anything at all. This is one of the strangest tensions in modern science. A theory can be incredibly successful and still leave the deepest question untouched. Quantum mechanics predicts the behavior of atoms, light, electrons, magnets, chemical bonds, lasers, semiconductors, and countless technologies that shape daily life. It explains why atoms have stable energy levels, why materials absorb and emit certain colors, why electrons can form patterns that classical physics could never predict, and why the microscopic world does not behave like a tiny version of the world you see. In practical terms, it works so well that much of modern technology depends on it. But when you ask what the quantum state really is, why measurement gives one outcome instead of another, why the laws have this form rather than some other form, or why there is a reality governed by these rules in the first place, the theory becomes less like a final answer and more like an extremely precise map with the origin of the map left unexplained. It can say, if you prepare the system this way, these are the possible results, and these are the chances. It can tell scientists what patterns should appear in experiments and how matter should behave under certain conditions. But prediction is not the same as ultimate explanation. A clock can tell time without explaining why time exists. A map can guide you through a city without explaining why the city was built. In the same way, quantum mechanics guides us through the microscopic world with breathtaking precision, while still leaving room for competing interpretations about what is happening beneath the predictions. Some interpretations treat the wave function as a real physical thing. Others treat it more like a tool for organizing knowledge. Some suggest that all possible outcomes continue in branching realities. Others focus on measurement, information, or the relationship between systems. The experiments agree with the mathematics, but the meaning remains debated. That is what makes quantum mechanics so humbling. It shows that science does not always move by turning mystery into simplicity. Sometimes it turns vague mystery into precise mystery. It teaches us how to calculate the behavior of reality before it teaches us why reality has that structure. And perhaps that is not a failure. Perhaps it is a reminder that understanding has layers. First you learn the pattern, then you learn how to use it. Then much later, you ask what kind of universe could make such a pattern possible. Quantum mechanics may be one of humanity's most powerful instruments of prediction, but it also stands like a doorway we have not fully crossed. It lets us build machines, explain atoms, and test nature with unbelievable care, while quietly refusing to answer the oldest question underneath all questions. Why is there something lawful, measurable, and real at all? The theory predicts the notes, but not why there is music. It describes the rules of the game, but not why the game exists. And in that silence, the universe does not become less scientific. It becomes deeper. reminding you that even the most successful knowledge can still end at the edge of wonder. The past may not be as fixed as it feels in every interpretation. The past feels like the one part of reality that should be safe from uncertainty, because whatever else the universe may hide, what already happened seems as if it must be finished. A cup fell or it did not. A particle went left or right. A signal arrived before another or after it. Your mind depends on this firmness, because memory, responsibility, history, and identity all lean on the belief that the past is a closed book. But quantum physics makes that confidence more delicate, especially when scientists ask what happened to a tiny system before it was measured. In ordinary life, the past becomes fixed because the world leaves countless records. Footprints remain in dust, heat spreads into a room, light scatters off surfaces, memories form in brains, cameras store images, and broken things do not quietly return to their earlier state. These records make history stable. They give the past weight. But in carefully controlled quantum experiments, where a system is isolated enough that the environment has not yet forced a clear record, the question, what really happened before we looked, can become surprisingly difficult. Some interpretations say the quantum state represents real possibilities evolving together until measurement produces a definite result. Others say the wave function is more like a tool for predicting what observers can know. Some approaches, like consistent histories, allow different possible descriptions of a system's past, but only certain sets of histories can be discussed together without contradiction. Delayed choice experiments make the strangeness feel sharper. The way a particle is measured later can determine whether it is meaningful to describe it earlier as having behaved more like a wave or more like a particle. This does not mean a human can magically rewrite yesterday, and it does not mean your personal past is changing whenever someone asks a question. That would be misleading. The careful point is stranger and more precise. At the quantum level, before a lasting record exists, the past may not always have the same kind of definite, classical shape we assume from daily life. The universe may not carry a hidden movie reel of every tiny event in the familiar way, waiting for us to rewind and watch. Sometimes what can honestly be said about the past depends on the measurement, the record, and the framework used to describe it. Once information has leaked into the environment and become practically irreversible, history becomes stable enough for the ordinary world. Fossils, scars, photographs, memories, ruins, and stars all become records of what happened. But before that hardening, reality may be less like a completed diary and more like a set of possible stories that only become a single usable history when the world leaves evidence behind. And perhaps this is why the past feels both solid and mysterious. At human scale, it is fixed because records hold it in place. At the quantum edge, it may be more subtle because definiteness itself can depend on interaction. Vacuum decay is the most terrifying theoretical possibility. Vacuum decay is terrifying because it does not imagine the universe being destroyed by something inside space, but by space discovering it was never in its final state. The idea begins with a strange question. What if the vacuum we live in is stable enough to last, but not the deepest possible condition of reality? In physics, a vacuum is not absolute nothing. It is the lowest energy state available to fields, or at least what appears to be the lowest state from where we stand. But some theories allow a disturbing possibility called a false vacuum, a condition that looks stable, behaves normally, and can persist for an unimaginably long time, while a lower energy state exists somewhere beneath it, in the deeper landscape of physical possibilities. If the universe were in such a false vacuum, then in principle, a tiny region could someday shift into the lower state, forming a bubble of new vacuum. That bubble would not be an explosion in the ordinary sense. It would be a change in the rules of the fields themselves, expanding outward through space at nearly the speed of light. Inside it, the values of fundamental fields could be different, which means the properties of particles, forces, atoms, and chemistry could change. Matter as we know it might not be able to exist in the same way. The frightening part is not just the scale, but the silence. If a vacuum decay bubble were moving toward us at light speed, no warning signal could arrive before it, because nothing could outrun it to tell us it was coming. One moment, reality would be normal. The next, the underlying rules might be different. But this must be said carefully, because the idea is theoretical, not a prediction that disaster is waiting nearby. Measurements connected to the Higgs field have led some physicists to discuss whether our vacuum could be metastable, meaning long-lived but not absolutely final. Yet even if that is true, the expected lifetime could be vastly longer than the current age of the universe. There is no evidence that vacuum decay is about to happen, and it is not something ordinary human technology is known to trigger. Its terror is philosophical as much as physical. It shows that even the background of existence, the thing we treat as the most reliable stage of all, may have hidden conditions beneath it. Stars can die, galaxies can fade, black holes can evaporate, but vacuum decay asks a deeper question. What if the laws that make all those stories possible are themselves resting on a state that might not be permanent? The universe then becomes less like a finished building and more like a balance that has held for billions of years, perhaps forever. Perhaps not because it must, but because it has not yet found a path to something lower. And maybe the most haunting lesson is not that we should live in fear. It is that reality's stability is not the same as simplicity. The world feels solid because its rules have been faithful every second of your life, every second of human history, every second since stars began forming. But physics leaves open the humbling possibility that even this faithfulness may be a condition, not a guarantee. Vacuum decay is terrifying because it turns emptiness into a question and asks whether the quietest thing in the universe might one day decide what all things are allowed to be. Consciousness may be the hardest part of reality to explain. Consciousness is the one part of reality you can never step outside of, because every question you ask about it is already happening inside it. You can study a star from far away, measure an atom through an experiment, scan a brain with machines, record electrical activity, track blood flow, observe behavior, and compare patterns of sleep, attention, pain, memory, and awareness. But the moment you ask why any of those physical processes feel like something from the inside, science reaches one of its deepest limits. A brain is made of cells, chemicals, electrical signals, blood vessels, proteins, and networks that change every second. We know that damage to certain brain areas can alter personality, memory, language, vision, emotion, or the sense of body ownership. We know that anesthesia can switch conscious experience off in a controlled way, that sleep changes awareness, that attention shapes what enters experience, and that brain activity is closely connected to what a person reports feeling. These facts are real and powerful. They show that consciousness is deeply tied to the brain, not floating separately in some easy magical space. But they still do not fully explain why brain activity should produce the feeling of being alive. Why should signals moving through neurons become redness, pain, music, fear, warmth, selfhood, or the quiet sense that I am here? A camera can process light without seeing. A thermometer can respond to heat without feeling warmth. A computer can store information without necessarily having an inner world. So what changes when matter becomes conscious? This is sometimes called the hard problem of consciousness, but the phrase matters less than the puzzle itself. The outside view of the brain is measurable. The inside view is lived. From the outside, scientists can describe neural firing, communication between regions, and patterns of activity. From the inside, there is taste, color, memory, silence, longing, and the strange private glow of experience. The gap between those two views is not easy to close. Some theories suggest consciousness emerges when information is widely shared across the brain, allowing many systems to access the same content. Others focus on how integrated and unified information becomes. Others argue that consciousness may depend on prediction, attention, embodiment, or the brain's model of itself and the world. Each idea reveals something useful, but no single explanation has ended the debate. And maybe that is because consciousness is not just another object in the universe. It is the condition through which objects appear to us at all. You never experience a world without experience. Even doubt, confusion, disbelief, and curiosity are forms of consciousness. That makes it slippery, intimate, and almost impossible to hold at a distance. Still, the mystery should not make us abandon science. It should make us more precise, more humble, and more patient. The brain is not simple, and experience may not have one tiny switch hidden inside it. Consciousness may arise from organized activity across the living brain and body, from layers of sensation, memory, attention, emotion, and self-modeling working together so smoothly that a world appears and someone seems to be inside it. But even if we map every pathway, a final question may remain. Why does this organized activity feel like anything at all? That is why consciousness may be the hardest part of reality to explain. It is not far away like a galaxy, not tiny like a particle, not hidden in ancient cosmic darkness. It is closer than your breath, closer than your thoughts, closer than the voice silently reading these words. It is the light by which every other mystery is seen. And perhaps the reason it is so difficult to explain is that we are not merely studying it. We are made of it while we ask. The laws of physics may depend on the state of empty space. The laws of physics may feel eternal, but some of what we call law may depend on the hidden condition of the vacuum itself. This is a difficult idea because empty space seems like the last place you would look for the source of rules. You might imagine laws as something written above the universe, fixed forever, untouched by stars, particles, heat, or history. Gravity behaves this way, light behaves that way, particles have certain masses, forces have certain strengths, and reality simply follows the script. But modern physics suggests a more subtle picture. The vacuum is not just blank emptiness beneath the laws. In some cases, it may help determine how those laws appear. A field can have a background value even when no ordinary particles are present, and that background can shape what particles are allowed to be like. The Higgs field is the most famous example. Its non-zero presence throughout space is part of why many fundamental particles have mass. If the Higgs field had settled into a different state, the masses of particles could be different. Atoms might not form the same way. Chemistry could change, and stars, planets, water, and bodies might never appear as we know them. In the early universe, conditions were extremely hot and dense, and some fields may have behaved differently than they do now. As the universe expanded and cooled, fields could settle into new states, a process somewhat like water freezing into ice, except far deeper. Not a change in ordinary material, but a change in the background conditions that define how particles and forces behave. Physicists call these changes phase transitions, and they may have shaped the universe's structure in its earliest moments. This means the laws we observe may not be only abstract commands. They may be connected to the state that space itself occupies. The vacuum can act like a setting on reality, not in a simple mechanical sense, but as a deep physical condition that influences masses, interactions, and possible forms of matter. This does not mean the laws randomly change around us from day to day. The vacuum we live in appears extraordinarily stable across all observations, and the rules of physics are consistent enough for atoms, clocks, galaxies, and life to persist. But the deeper possibility remains. What feels like permanent law may be the behavior of reality within one particular vacuum state. In another vacuum state, if such states are physically possible, the universe might not merely contain different objects. It might have different basic possibilities. Electrons might not have the same mass. Forces might not balance in the same way. Atoms might be impossible, or matter might organize into forms no mind like ours could imagine. This is why empty space becomes so important. It is not only the stage where laws operate, it may be part of why the laws take the form they do. The ordinary world feels secure because the vacuum beneath it is quiet, stable, and consistent. But beneath that quiet is a profound lesson. Reality may not be built only from things inside space, but from the state of space itself. The laws of physics may be less like commandments carved outside existence, and more like the behavior of a universe living in a particular condition. a condition so steady that we mistake it for absolute necessity. And perhaps that is the most unsettling part. The rules that make your body, your memories, the stars, and every atom possible may depend on the silent background you once thought was nothing. Space, time, fields, and information may be entangled ideas. Space, time, fields, and information may look like separate ideas, only because the human mind learned to divide reality into easier pieces. You are used to thinking of space as where things are, time as when things happen, fields as invisible influences spread through space, and information as what can be known, stored, or communicated. Each word feels like it belongs to a different drawer, but at the deepest edge of modern physics, those drawers begin to slide into one another. Space is not just a container, because in relativity, it can bend, stretch, and respond to energy. Time is not just a universal clock because its rhythm depends on motion and gravity. Fields are not just invisible decorations added to matter, because matter itself can be understood as excitations of fields. Information is not merely a human message, because physical systems carry states, correlations, and records that decide what can be predicted and what can be recovered. The strange possibility is that these four ideas may not be independent foundations. They may be different faces of one deeper structure. In black hole physics, for example, information becomes impossible to ignore, because what falls into a black hole seems to challenge the idea that physical information is never truly lost. In studies of quantum entanglement, some physicists have found clues that the connectedness of quantum states may be related to the shape and connectivity of space itself. This does not mean we already know that space is literally made of information, or that time is simply data, or that fields are only code. Those claims would be too strong. The honest version is more careful and more powerful. Several leading ideas suggest that space-time, quantum fields, and information may be linked so deeply that none of them can be fully understood alone. A region of space may not be just there. It may be defined partly by relationships between physical degrees of freedom. A moment in time may not be a flowing substance. It may be part of how changes and correlations are ordered. A field may not be a thing sitting inside space. It may be one way the deeper structure of reality shows activity. Information may not be an abstract extra. It may be tied to what physical states are possible, how they transform, and what traces they leave behind. This is why the frontier of physics feels less like searching for smaller and smaller building blocks and more like discovering hidden connections between concepts we thought were separate. The universe may not be built by placing particles into space, running them through time, letting fields act on them, and then writing down information afterward. It may be that space, time, fields, and information arise together, each one helping define the others. If that is true, then reality is not a stage, a clock, a substance, and a record layered on top of each other. It is a woven structure where location, change, activity, and knowable state are entangled at the root. And perhaps that is why the deepest theories are so difficult to picture. Your imagination wants objects in places, moving through moments, carrying properties. But the universe may begin before those categories separate. What you call space may already contain information. What you call time may depend on change. What you call matter may be field activity. What you call reality may be the stable appearance of a deeper web, whose threads cannot be pulled apart without losing the pattern. The more closely physics listens, the more the universe seems to whisper that its foundations are not isolated words, but one sentence too deep for ordinary language to say all at once. The universe may not be built from objects at all. The universe may not be made from objects in the way your hands taught you to believe. A child learns reality by grabbing, dropping, stacking, breaking, and naming things. Stone, cup, hand, tree, star. The mind grows around the feeling that existence is a collection of separate pieces, each one sitting somewhere, each one carrying its own identity, each one waiting to be moved, touched, counted, or owned. But the deeper science goes, the less this picture looks like the final truth. At the smallest scales, physics does not find tiny versions of everyday objects hiding underneath bigger ones. It finds fields, states, interactions, symmetries, probabilities, energy, and relationships that only become object-like under certain conditions. A particle can be detected as a single mark, but the theory behind that mark may describe something spread across possibilities before the interaction occurs. An atom can behave like a stable unit, but its stability comes from quantum rules, electromagnetic attraction, nuclear forces, and the allowed arrangements of its parts. A chair feels like an object because countless atoms hold a pattern long enough for your body and brain to treat it as one thing. But chair is not a fundamental ingredient of the universe. It is a useful name for a stable arrangement. The same is true, at different levels, for a cloud, a flame, a wave, a cell, a planet, and even a galaxy. These things are real, but their reality may be more like a maintained pattern than a final building block. Modern physics often suggests that objects are not where explanation begins. They are where explanation becomes convenient for minds like ours. We call something an object when its boundaries are stable enough, when its behavior is predictable enough, when its pattern lasts long enough to be tracked through time. But beneath that stability, the world may be made of processes that do not divide themselves into neat little things. A magnetic field is not an object you can place on a shelf, yet it can move a compass needle. Space-time is not an object in the ordinary sense, yet its curvature can guide planets and bend light. A quantum state is not an object with a visible surface, yet it can determine what outcomes are possible. Information is not an object like a stone, yet without physical states carrying differences, no structure could be specified or remembered. This means the object-based view of reality may be a practical interface, not the deepest architecture. Your brain needs objects because objects help you survive. It is useful to see a tiger, not a temporary arrangement of biological processes. It is useful to see food, not a chemical system exchanging energy. It is useful to see a cliff, not a gravitationally bound pattern of minerals. But usefulness is not the same as fundamentality. The deeper universe may be less like a box filled with things and more like a web of activity, where temporary forms appear when relationships stabilize. A wave on the ocean is not separate from the water, but it can still knock down a boat. A whirlpool is not a solid object, but it has a shape, a lifetime, and an effect. A flame is not a thing in the same way a rock is, yet you would never say it is unreal. Maybe much of reality is like that. Real patterns, not ultimate objects. The mistake is thinking that only hard, separate, lasting things deserve to be called real. The universe may be deeper than hardness, deeper than separation, deeper than the visible edges your senses trust. What exists may be events becoming patterns, fields becoming excitations, information becoming structure, and relationships becoming stable enough to look like things. And perhaps this is the quiet shift that changes everything. Reality may not be a pile of cosmic furniture arranged inside space. It may be a living order of transformations, where objects are the slow, familiar shapes that deeper processes wear when consciousness finally looks at them. Reality may be what appears when the invisible becomes organized. Reality may be what appears when hidden patterns become organized enough for a mind to recognize them. At first, this sounds almost too abstract, because the world in front of you does not feel like organization. It feels like things. A face is a face, a mountain is a mountain, a body is a body, a star is a star. But when you look more carefully, every familiar object is the visible result of invisible structure holding together. A crystal appears clear and solid because atoms are arranged in a repeating order. A living cell appears as a tiny unit of life because molecules, membranes, proteins, water, and electrical gradients are organized into a system that can maintain itself. A galaxy appears as a glowing island because gravity has gathered stars, gas, dust, and unseen mass into a long-lived pattern. Even your own thoughts appear as feelings, images, decisions, and memories only because billions of neurons and signals are organized into meaningful activity. The parts alone are not enough. A pile of letters is not a poem. A pile of notes is not a song. A pile of atoms is not automatically a living body. What makes something appear as a real, recognizable thing is the way its hidden ingredients are arranged, constrained, connected, and allowed to act together. This is why organization may be one of the deepest bridges between the invisible and the visible. Fields are invisible until their effects become patterned. Information is invisible until it is stored in a physical state. Forces are invisible until motion reveals them. The structure of an atom is invisible to ordinary sight, yet it decides chemistry. The structure of DNA is invisible to the naked eye, yet it helps guide how living organisms build proteins and pass traits forward. The structure of space-time is invisible in daily life, yet massive objects reveal it through curved paths, bending light, and gravitational waves. Again and again, reality does not show itself first as raw essence. It shows itself as organized behavior. This does not mean that everything is just a mental illusion. A hurricane is real, but it is not a separate solid object. It is organized air, heat, moisture, pressure, and rotation. A flame is real, but it is organized chemical transformation. A self is real, but it is organized memory, body sensation, prediction, emotion, and attention. A thing becomes something when change is structured enough to leave traces, affect other systems, and remain coherent across time. Maybe this is why the universe can feel so solid while being built from layers that are not solid at all. The visible world is not the opposite of the invisible. It is the invisible becoming stable enough to appear. And perhaps that is the final quiet lesson. Reality may not begin as finished objects waiting to be named. It may begin as possibilities, fields, relations, differences, energies, and rules. And only when these hidden ingredients become organized do they rise into the forms you can touch, see, remember, and call real. The universe may be less like a collection of things and more like an immense act of pattern making, where the unseen becomes structure, structure becomes experience, and experience becomes the world you wake up inside. Quantum physics breaks common sense at the smallest scales. Common sense begins to fail the moment reality becomes too small for your hands, your eyes, and your everyday instincts to follow. In the world you live in, objects seem to have clear locations, clear identities, and clear histories. A cup is on the table, or it is not. A stone follows one path when it falls. A door is open or closed. This way of thinking works so well at human scale that it feels like truth itself. But quantum physics reveals that it is only a local habit, a rule of thumb shaped by large objects, warm environments, and slow senses. At the smallest scales, nature does not behave like a collection of tiny familiar things. It behaves according to rules that are precise, tested, and deeply successful, yet almost impossible to picture with ordinary imagination. An electron is not simply a miniature planet orbiting a tiny sun. A quantum system does not always carry every property in a definite way before it is measured. Possibility is not merely ignorance. It becomes part of the physical description. In some experiments, what can happen must be treated as a spread of potential outcomes, and only interaction with the wider world produces the single result you finally observe. This is why quantum physics feels so strange. It does not break because it is vague. It breaks your intuition because it is accurate in a region your intuition was never built to handle. Your brain evolved to throw stones, avoid danger, recognize faces, and move through solid surroundings. It did not evolve to imagine probability waves, uncertainty, or systems whose measurable features depend on how they are tested. Yet without these strange rules, the ordinary world would not exist in the form you know. Atoms would not have stable structures. Chemistry would not work the way it does. Materials would not have their familiar properties. The light from screens, lasers, solar panels, semiconductors, and medical imaging would not make sense without quantum principles behind them. The weirdness is not locked away in distant laboratories. It quietly supports the technology around you and the matter inside you. The mistake is thinking that common sense is the deepest layer of reality. Common sense is more like a simplified map, useful for walking through the visible world, but not detailed enough for the foundations beneath it. Quantum physics asks you to accept something humbling. Reality is not obligated to be imaginable before it is real. The universe can be lawful without being intuitive. It can be understandable through experiment and mathematics, while still resisting the pictures your mind wants to draw. And maybe that is the real lesson at the smallest scales. Nature is not confused. We are simply meeting a level of the world where the language of everyday life becomes too blunt, and where truth survives even after common sense falls apart. You do not see the world directly, you see a reconstruction. You never meet the world in its raw form. You meet the version your brain has already translated for you. This is difficult to feel because vision seems immediate and honest, as if your eyes open and reality simply pours in. But your eyes are not windows in the simple sense. They are living sensors that catch light and convert it into electrical activity, and from there, the brain must build the experience you call seeing. The outside world does not arrive as trees, faces, depth, color, motion, and meaning. It arrives as scattered signals, different wavelengths of light, shifting contrasts, edges, shadows, and changes across the retina. Your brain then organizes those signals into a stable scene. It decides where one object ends and another begins. It estimates distance from tiny differences between the two eyes. It creates the feeling of depth from flat images. It separates movement from stillness, recognizes familiar shapes, and attaches names and meanings before you consciously think about them. You do not see a chair as a collection of light patterns. You see chair because your brain has already turned sensation into interpretation. This reconstruction happens so quickly that you mistake the final model for the world itself. And yet the model is not a perfect copy. It is selective. Your brain sharpens what matters, softens what does not, ignores some details, emphasizes others, and uses memory to guess what should be there. This is why a shadow can look like a person for 1/10 second. Why a familiar face can appear in a pattern. Why a moving object may seem continuous even though your eyes jump in rapid bursts from point to point. The world you experience is not fake, but it is processed. It is more like a live translation than a direct recording, and every translation makes choices. Your senses give the brain evidence, but the brain gives that evidence structure. It creates a usable reality, not an unlimited one, because unlimited detail would overwhelm you. You need a world you can act inside, not a perfect inventory of every photon and surface. That is why perception is useful before it is complete. It helps you reach for a cup, read emotion in a face, avoid danger, follow movement, and recognize home. But the price of that usefulness is humility. What feels obvious may be edited. What feels direct may be assembled. What feels like the world out there is actually the world after passing through the quiet architecture of your nervous system. So when you open your eyes, you are not simply seeing reality. You are seeing reality rebuilt into a form your mind can survive, understand, and call real. Gravity is not really a force in Einstein's picture. Gravity feels like a force because your body is always being stopped from taking the path it naturally wants to follow. Stand on the ground and you feel weight pressing through your feet, as if Earth is pulling you downward with an invisible hand. That picture works well enough for everyday life, and Newton's description of gravity as an attractive force remains incredibly useful for calculating many motions. But Einstein's deeper picture changes the meaning of the pull itself. In general relativity, gravity is not treated as an ordinary force reaching out through space like a rope. Instead, massive objects such as planets and stars change the geometry of space-time, and other objects move along the straightest possible paths within that curved geometry. The strange part is that those paths can look curved to us. The moon does not orbit Earth because it is being yanked sideways in the simple way a ball on a string is yanked. It is moving through curved space-time, following a natural path that keeps bending around Earth because Earth's mass has reshaped the stage around it. A falling object is not being forced downward in Einstein's view. In a sense, it is doing the most natural thing it can do. It is the ground that interrupts that fall. When you stand still, the surface of Earth pushes up on you, preventing you from following the free-fall path your body would otherwise take. And that upward push is what you feel as weight. This is why astronauts in orbit feel weightless, even though gravity has not disappeared. Earth's gravity is still strong where they are. They are weightless because their spacecraft, and everything inside are all falling together around Earth, constantly missing the ground. Nothing inside the spacecraft is being pressed against a floor in the ordinary way, so the familiar feeling of weight vanishes. This idea is not just poetic. It has been tested through the bending of starlight near the sun, the timing of signals near massive bodies, the behavior of planets, and the gravitational waves detected from distant cosmic collisions. Einstein's picture teaches that gravity is not merely something objects do to each other, but something matter and energy do to the shape of reality itself. And that should make even standing still feel strange. The floor beneath you is not simply supporting a body in a force field. It is stopping you from moving along the curved path space-time has quietly offered you. What you call gravity may be the feeling of being held away from your natural fall. A reminder that reality is not a flat stage with forces painted on top, but a flexible structure where motion, mass, space, and time are woven together so deeply that even down becomes a geometry you can feel in your bones.